आया नहीं कृपया, आया नहीं कृपया, चेक करके मुझे बताना है। किससे भेजा आपने? अरे चेक कर लो, फोन पे आ गया होगा यार। फिर आप बोलोगे, फिर वाला, फिर
फ्लैग मार्क किया गया, उसकी तस्वीर आपको दिखा रही हूँ।
Yeah, Dr. Kamlesh, are you here? Hello?
Audible?
Yes,
Hello.
you are audible. So, Dr.
Just-
Kamlesh is here. So, Sanjana, please start.
Anurag sir, just give me a second. I would try to join from one more device and try to share my screen. Just give me a second.
Okay, sir.
Yes, whenever you will join, please let me know. So, joined? Have you joined? Should we start, Dr. Kamlesh?
Yes, sir, we can start. Yes.
Sanjana, can you start now?
Yes, sir. Thank you so much, sir.
Please.
Good evening, everyone. Good evening, everyone. Welcome back to day 3 of our FDP program, Generative AI Technique, Tools and Application. I hope you all are as excited as I am for another day filled with learning and inspiration. Without further ado, let's jump into today's keynote session. Now it's my honor to introduce our first keynote speaker of the day, Dr. Kamlesh Tiwari. They will enlighten us on adversarial training for generative modeling. Dr. Kamlesh Tiwari is an associate professor in the Department of Computer Science and Information System at Birla Institute of Technology and Science, BITS Pilani campus. He earned his PhD from the Department of Computer Science and Engineering at the Indian Institute of Technology, Kanpur in 2016. Dr. Tiwari research interests including machine learning, deep learning, artificial intelligence, computer vision, and multimodal biometric, focusing on modalities such as fingerprint, face, palm print, knuckle print, forehead, teeth photo, and footprint. He has published over 80 research articles in journal, conferences, and book chapters, contributing a significant to this field. At BITS Pilani, Dr. Tiwari is affiliated with APCAR and leads the Map My India AIML lab. He co-in-charge the Advanced Data Analytics and Parallel Technologies Lab, and they actively participate in the Multimedia and HCI Laboratory. As a member of IEEE and Signal Processing Society, he remains engaged with the broader research community. In addition of his academic role, Dr. Tiwari co-founded Cognex Technologies, reflecting his commitment to bridging academic research and industry application. His dedication to teaching and research continues to inspire students and colleagues. Now it's my request to Dr. Kamlesh Tiwari to kindly take on the stage. Let's give him a warm virtual applause for the presentation.
So, Dr. Kamlesh, you are welcome by virtual
Thank,
clapping.
thank you, Sadhana. Thank you very much for the generous
Okay, okay.
introduction. Hope I am audible well. So,
Yes, sir.
thank you. First of all, I thank all the organizers for organizing such a great event, and it is really a honor for me and to be part of this session and to be in front of you saying some words of wisdom, whatever is possible from my side. So this is a great opportunity for me, and I also encourage all of you to please participate as much as possible, because these kind of sessions, when very lot of experienced speakers and very good uh, learners are also there. You can learn with each other. With you can learn with their experiences, and this actually adds a lot to the everything. Thank you, everyone. Thank you, NIT Delhi. Thank you, everyone, for providing me this opportunity to be in front of you. So today we are going to talk about the adversarial training for the generative modeling, and I am Dr. Kamlesh Tiwari from BITS Pilani, and this is my campus, and this is the NIT Delhi campus. If you have been offline, maybe you may have witnessed this beautiful campus of NIT Delhi. So once again, let us start our discussion. So before starting this, I would just request everybody to, if possible, can you just type hi on the link, so that I can just see that at least few people are able to write. So whenever is required, we can just talk about that, and then you can type and we can see that hi. Yes, I can see that hi from Arjun and Inder Singh ji and many other people. Yeah, thank you. So in the while this session is on, if you want to ask any kind of question, please stop me any point of time. You can type any kind of message, and I hope you are also allowed to
Hello,
speak.
hello.
Then you can
Um,
you can also speak whenever is required. So all right, thank you. So we are going to talk about today about the adversarial training for the generative modeling. So essentially, what I wanted to mean here, that what is the effect of adversarial training to improve the generative modeling setting. Okay, so without adversarial training, what is going to happen, and with the adversarial training, what is going to happen is actually our the subject matter. So today we are going to see that when we apply adversarial kind of training, what it actually gives you more important. Okay, so so in a sense, we would be trying to see that what is the generative modeling in a broad term, and we would start by VAE, which is actually a very important uh, component, that actually the first component that actually try to generate something. We are going to see that how it generates anything over there. Then we would see that how what changes are actually we have done into the GAN with respect to the adversarial training, and how it becomes effective, and now we are going to using all these things. So this is what our subject matter is today's discussion. I would try to be very basic. So anything that you means, I would start from very fundamental. So anything that comes in your mind, you please feel free to ask me, and I would try to be very simple in that particular term. Okay. All right. So so the actually the things start with the autoencoders. Okay. The first idea is actually autoencoders. So autoencoders are a special kind of architecture, uh, basically neural networks, that given an image try to generate the same image. Okay. So think about a neural network that when you provide an image, say A, it try to generate the same image A. Does it make any sense? Does it make any sense? Because this image is given to me, why I am going to generate the same image? Okay. If I want to generate the same image, it doesn't make any sense. Nahin? Anybody? So actually the idea is that only generating the image is actually not important. This structure is actually more important. Okay, that whatever neural network I am going to come up, it may be possible that that I take all the bits which are there inside my image over here, and I also get the same number of bits which are actually given to me as an output. But in between, I can do lot of juggling. Okay. In between, I can do lot of changes. So one change could be possible that let's assume that the image is only 10 cross 10 for just for sake of clarity. So 100 values are going to get inside. 100 values are going to get inside, and at the output also I need 100 values. But here the first layer I can put say 150 neurons. So what would happen that these 100 things are going to interact with 150 things, and now there would be some non-linear kind of action is going to happen. Okay, then after that 150 let me put again 120, then after that let me put 80, then after that I put 50. Let's assume I fit 50 neurons, they all are fully connected. After that again if I put a t and I put 100 and 120 120 and 150 and then 100, then I am going to get the same thing output. I'm going to get the same thing as an output. So essentially here when 100 things were there, from this 100 I make 150, then I make 120, then I make 80, then I make 50. So these things are going to reduce this something, whatever 100 thing to 50. And after that, if same thing is over here, I can say that, for example, 80, 120, 50, 150 again, 100 again. So this particular structure looks like that everything, whatever from the output direction you just see. Okay, this 100 thing dimension thing has been generated from this one only. Yes or no? This 100 size item has been generated from this thing only, which I can say that the, let me say the hidden representation. Okay, so 100 values I have actually inputted, and after that I got 50 things. Okay, and from 50 this had been generated. Okay, the question is it possible? Again, the question is very serious because I don't know that whether I can generate it or not. Okay, so similarly, very simple circuit, which actually I started to talk about, that it is a neural network. It is a neural network which, given an image, generate the same thing, is actually not that straightforward. There is a definitely a problematic area where I can say that there is something which is going to generate one thing. Say that it is encoder. I can say that there is some encoder, and there is some part which is going to decode. Means using this, it can again create the actual image. So there are two different parts, and in between there is a hidden representation. So technically, I can say that if I say that in terms of the function, because now if we actually define everything as a function, we can say that this is a function f, this is a function g. Then I can say that whatever image I am going to give, function of this is going to be the h. Okay, h is what? Function of that thing, and on that I apply the g and I get what? Same image. So this is the equation. Actually, this actually I wanted to do. One thing you should try to focus that if it is possible. However, I'm not telling that how I'm going to do that. But if let's assume that if somehow it can be done, then a very important thing we have achieved. What is that? That here 100 values were there, but I had represented the same thing using 50 values, and out of these values, it's a perfect representation because out of these 50 values, again I can generate those 100 perfectly. I can generate the same 100 values. Okay, this is a very interesting architecture called autoencoder. Any questions on that? So the architecture that we have talked about is generally referred as a undercomplete autoencoder. Undercomplete means 100 values were there, then I can reduce it to lesser value, say 80, then 70, then 50, then maybe 30. Okay, it is going to be sequentially going to reduce the size. But it may be also be possible that sometime I can tell that in here 100 value, few minutes back we had talked about 100 values were there, then I make it 150. Then from that I reduce to 120. From this I reduce to 80, and after that I make it 50 or 30, whatever. So sometime I can in between I can increase also. So do you think that if I do it, so this is actually something like that you are actually throwing the thing into the higher dimensional space, and from the higher dimensional space then you are going to take the things back. Have you seen that this somewhere where this kind of application have you seen somewhere? Okay, have you seen some kind of application of these kind of things? Hmm? In SVM, na? In SVM you may have thought about that there are kernel function, and what kernel function do? They project your data to the higher dimensional space, and from higher dimensional space actually they give you the similarity and similar kind of thing. So if you increase it initially and after that you actually reduce, so you get these kind of effects, something like that, the kernel functions into the system. So all right, so what my setting is that we are going to have this kind of system where we have a function f, and from this we get a hidden implementation, from this we got this, and this actually we are going to get. So how can we make this system? Is if I want to make a system which actually x is actually to this input and output are same. For that we don't actually we don't care much about that. Okay, when we make the architecture, we actually rely on the back propagation. We say that if everything is fine, I wanted this kind of output, maybe using the different kind of gradients which are actually available. If the back propagation work, it would be able to find out the solution for me. Okay, but if you have any questions, yeah, please keep asking if you have any questions. Okay, so in general setting, what happens that there is something called the back propagation, and actually this is what the very important part of the neural network, that when the back propagation came first time around 1980 1988 or so. So after that the things started working once again, and then we have, after that we have not seen that from we have never turned back, and we told that no, I don't want to explain that how to find out the parameter. Back propagation is the way it is automatically going to find out the right parameter. If I say that I want this value to be here, it is a responsibility of back propagation. Whatever is possible, it would be able to change our parameter so that this input becomes output. Is it right? Is it correct? So in this setting, when I'm telling that you give me this particular hidden representation, this hidden representation can be directly thought about thought as a PCA, principal component analysis, because in the principal component also, you know that if a lot of values are available, we can tell that instead of using all those values, using lesser number of value, also we can do the same kind of task. So it is something like the PCA, but definitely it is going to be better than PCA. We are going to see about that. Okay. Uh, one more important thing that we can think of. Yes, any questions? Is that when you find out the smaller representation. For example, in our running example, I was telling that the image has 100 pixel, but now we have converted to the 30 pixels only. But this 30 pixel is very important because it actually very precisely represent all the information which are there into the 100 bits. So if we want to develop a classifier, for example, for any class classifier, so developing on this particular original data and developing, if you compare the developing on original data and developing on this hidden representation, looks like that this hidden representation going to be the better. Okay, so this small size can be treated as a feature of this image. Okay, can be treated as a feature of the image, and then we can apply later whatever we want to do. We want to do classification, regression, or matching, whatever we want to do, we can perform these things over there. So end-to-end training could be done on the extracted features. Okay, whatever we wanted to do, matching, training the classifier, regressor, matching, segmentation, whatever we wish we want to do on that. Okay. Here are some example. This again a very interesting one where I'm going to supply an image, and then this is a architecture, and you know that popularly similar kind of architecture is called the unit. So at the end, what it gives you, that it gives you segmentation. Means you have trained the model in such a way so that if I give this image, give me this image, and now the parameters are changed in such a way so that with this respect to this image, you are going to get this image, and for multiple images you have actually trained, and then after that, whenever you supply a kind of image, you are going to get the segmentation for that new image, which actually not have been shown. This is a important application. This is another example of the autoencoder, and which is very interesting, and which actually says that you know that MNIST database, which is a digit database where images are only 28 cross 28, and 28 cross 28 means 784 number of bits. So in this small area where 28 cross 28, 1, 2, 3, 4 numbers are actually written. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers are actually written. So this database, for this database, actually there are 784 values. So I can reduce them using some method. For example, if I apply the PCA, okay, so I can reduce this 784 to 30, and from this 30 I can again reconstruct this 784 because I know what are the loading values. Okay, sir, how do we determine the optimal number of layers and neurons in the autoencoder to balance the reconstruction accuracy and the computational accuracy? A very interesting question, very important question. I think this question somebody has asked. I cannot see the name. I think Pankaj. Okay, Pankaj had asked this question. So this is a very interesting question. I will just go back and come back here. So your question is that how to find out what is the optimal number of things over there. Okay, so look, your question is that how to find out uh, the parameters. Okay, so they are specialized kind of parameters, that how many neurons are they are called hyperparameter. How to find out the hyperparameter, how hyperparameter tuning, and the only way is to do the tuning. Okay, the way is to do the hyperparameter tuning. Maybe with a smaller amount of data, you change the architecture one by one and do iterations, and by this you would be able to find out that what is the good architecture. Okay. So what I was telling here, I was telling that we have a MNIST database where digits are actually provided to me. Digits are actually provided to me, and I wanted to reduce this 784 because it's a big number to the smaller number, maybe good feature. Let me say 30. So I can apply PCA. So I can apply and find out the 30 best parameters, and then from these 30 best parameters, again I can reconstruct this 784 values. Okay. So different thing could be that instead of using this direct PCA method, I can apply the architecture. So I say that from 784, I put 1000, then 500, then 250, then 30. Okay, this is autoencoder architecture. After that, this three again, this 30, 250 again, 250. Then after that 500, then after that 1000, and then after that 784. I took output. This is the encoder decoder network has been constructed. So so see the output. So this is the real data. Okay, this is the real data. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. If I do this kind of reconstruction, means I feed 2 and output also I get 2. So I got this 2. Can you tell me which 2 is better? If I say that this is first one, this is second one, this is third one, which is better? Forget about third one. Just think about first and second. You can type on the chat 1 or 2. Second one, because you can see that here something is there, but which is not here. Okay. Similarly, 0, 1, 2, 3, 4, 5, 6. You can see that this second one looks like that. This second line actually is actually better than the first one from the original data. This data I have feeded, I got this data. This is better data. And with the PCA, you get this. You can see that it is a kind of blurred one, and it is not that good. Okay, so this is not good. So original data. So what is this? This is original This is autoencoder and this is PCA. So because of the inherent high degree of nonlinearity, autoencoder works excellent, okay, on this data. This is another example of the autoencoder where actually we wanted to find out the similarity between the documents. Okay, so how can we find out the document similarity? Document similarity, you can say that I have, let's assume that I have a document A and I have a document B. So first you create a list where you say that what are the different words in this there are, okay, how many different words are there. You just create important word, maybe is, am, or the, that, small words you can neglect. What are the important words? You just take the list of those words. So let me say that 2000 words I am going to consider. Okay, to consider the similarity between two documents, I have a dictionary where I am considering 2000 word. So what should be their representation for this? Okay, what should be the representation? So representation could be, because one hot representation could be there, means 2000 words are there, so I can take the same kind of method to find out the
Dr. Kamlesh Tiwari, sir, are you in the meet?
Uh, Dr. Kamlesh,
am I audible?
please unmute yourself. I don't know how it is muted.
I think it automatically got muted, sorry.
Uh-huh.
Okay, so please let me know if there is any issue. Okay, so what I was telling, so till what I was audible?
Yes.
Okay, so so what I wanted to tell that if I want to compare two different files, I just try to see that what are the different words between them, and then I can do the dot product and find out their similarity. Instead of using this kind of representation where I say that one hot vector representation, can I do better representation? Maybe a smaller size representation for every word. Can I find out a 10 bytes representation, a small representation? Can I do that? Again, using the same kind of method that few minutes back we have thought about, maybe PCA or any other method, we can again reduce the dimensionality and then we can apply the same kind of method. So if I use autoencoder to find out the reduced size, for example, 2000 word, then I say that using 2000 values, then I reduce it to 500, then reduce to 250, then reduce to 10, then again I increase it, and then I do the iteration over that, and then find out what the right representation. So, and then again apply the cosine similarity to find out the document. So it has been shown that these linear discriminators, actually their accuracy is only 30% on the database. On some database it has been actually tried to find out, but autoencoders where their accuracy was around 45%. Okay, and to visualize that how good this particular data is, so it looks like that. Look, this actually says the different data. So you can see that this one kind of data, maybe one kind of data is here, another kind of data is there, but you can see that a lot of mixing is there. This green is here also, red is also here. So but looks like that it is discriminating, but not that much. But when you do with this autoencoder, the data comes something like this. Can you see? Here you can see that lot of discrimination is there. Okay, it is very much discriminative as compared to the other methods. So so this is the one thing, this is one technical part that actually is very important, that what is autoencoders. Now I wanted to change this autoencoder in such a way so that I can find out new things out of this. Okay, how can I do that? So one method is that if you have a database, you give it to the encoder, you get the hidden representation, and try to plot that where these hidden representations are going to represent. Okay, definitely all the things would not be there, because in the hidden representation all the space would not be filled, but some space you know that this is going to be filled. Can you give me any other point from here? Can you give any other point from here, from this space? Can you give me any other point? So what is the problem? You can pick any point over here, but the issue is that whether it represents the something that is related to my database, that I'm not sure about this. If I feed this data to the discriminator, I would be getting some output. Okay, I may be getting some output. There is some question. There is someone. Sarojji, you have raised a question. Raise a hand. Please let me know. Please type the question whenever you have any question. Okay. You have any question, Sarojji?
May I ask, sir?
Yeah, please. Please.
Sir, it is from previous slides. I have a very basic doubt I want to discuss.
Which slide?
From PCA, where we were using, you were showing the MNIS data set. Sir, I
Mhm,
have a very basic question. I applied autoencoder to reduce the dimensions.
mhm.
And what actually I want to know, the image size was very large, and the memory I was having, RAM size, that was not enough to handle. So what I did, I reduced all the images which are of different sizes to a standard size of 128 by 128. And then I
No,
applied autoencoder. So
I
I
don't
got
understand.
confused.
120, 128. You want you increase to how much?
I had some images which were of
Mhm,
varying size and very large size.
mhm,
I
mhm.
reshaped all the images to 128 by 128.
Okay.
And then
Okay.
actually I was trying to find out uh, the latent space using autoencoders, reduce
Mhm,
dimension. So I
mhm,
applied autoencoder after that.
mhm,
So my doubt was regarding I already reshaped that to a small level, that is 128 by 128.
mhm, mhm,
So some features were already reduced, and then I applied autoencoder.
mhm.
So was it okay to do?
Yes,
Because
it was okay.
already I reshaped all the images,
No, let me tell you why. Okay. One thing is that if you have a larger image, if you have a larger image, you have
and all
reduced to
were
it.
uneven size.
No. When you have reduced to the smaller size, actually you are preserving the uh, visual appearance. Okay.
Yes.
When you are reducing the size, you are actually trying to preserve the visual appearance. But when you are going to convert it using autoencoder, then at that time maybe whatever thing you are going for 50 dimension or 500 dimension, whatever value you are going to get, that may not represent an image. So till now you have actually not find out any features. You only preserve that what is being seen into the image actually remains over there. If there is an elephant, it remains elephant. But right now this is the different representation of elephant. For example, if you can think it that way, that it is translated to the another language. For example, in Hindi, if I say that hathi, okay, so here it is hathi, but hathi actually is a representation of elephant. Okay, but it is not the same thing. Hathi is Hindi word, ELEPHANT or HANTHI. This is totally different as compared to the image of that particular elephant. So here you are actually trying to find out the feature which are actually going to represent that thing better, because how these features should be such that if you have an elephant and zebra and any other uh, uh, dog or cat, they should be very different to each other. Am I able to tell you?
Yes, sir.
So
Yes, sir.
these are actually features. So you go into the feature dimension, they here visual appearance doesn't matter. What matters is the better representation, so that their discriminative power is actually very high.
And then I fed it to the CNN
Correct.
for
No, then
classification.
No, then this is your, now you are doing a wrong thing.
So
You
what
must
should I
apply
do?
directly fully connected layers over here, because now you find out the features, na? The CNN
Yes,
actually try to extract the feature from images only, and now on the feature if you want to apply, then it becomes a problem. Am I
because
able to tell
already we
you?
have got the features through
Correct.
autoencoder.
You got this feature. So after autoencoder, whatever you got here, you should not apply the CNN. You can apply, for example, when your big image was there, na, from that you converted to the small image. At that time, you can apply CNN. From here, you can apply again autoencoder, and after that, you fully apply the fully connected layer.
Okay, sir.
Am I making
Okay.
sense?
Thank you, sir.
Because on the feature, if you apply CNN, you are actually trying to see that is there any visual appearance is there, and visual appearance is not there because you have extracted the feature. Okay.
Okay, thank you, sir.
All right. Thank you for the questions. Please keep asking. Okay. So here, what I wanted to explain you that if I have a database, let's assume the database of cat image. Okay. So I applied. Let's assume the system is actually already trained. So whatever feature I am going to get, I am going to represent into the feature space. Here, whatever images, for every image, I can find out where are the cat images, what is the feature of that cat image. But if I take anything that is actually not from here and feed it to the discriminator, it would definitely going to generate something. Whether that thing is cat, no, not sure. We cannot be sure about that because complete space is not good. Okay, complete space is not the cat. Cat would be somewhere, but other places there should not be cat. So there should be a way so that I can know that looks like the cat images are here, and I can then sample for that. If I can solve that this mystery, that how to sample from here, then I can insert that image to discriminator to get the new image of a new cat. Am I able to explain this part? Everybody, yes or no? Just type yes on the chat. Okay, try to type yes on this. So what I wanted to tell, if
Participant,
I
please unmute mute yourself and type in chat box only. Please
correct, correct,
don't unmute yourself.
yeah. So what I wanted to ask you, that if I can solve in some way that what is the distribution of this particular latent space, then somehow, because all the images are would not be, even if I know the distribution, even then all the images would not be with me, na? So I can sample any new point from this and supply to this discriminator and get a new image corresponding to that particular feature, and that could be a new cat that has not been seen. So to be generative, I have to solve this particular part. How to solve that particular part? Okay, how can I solve that particular thing? So one way is that look look what happens. There is a very important thing that I also want to tell you, that let's assume that this is the total space available for everything. Okay, here cat images would be only acquiring a small space. After applying the encoder, this would be converted to the new space, and in that space maybe a different kind of, for every point I am going to find out the corresponding image, corresponding place, so it could be a different shape. Okay, but if I leave this particular system by itself, it would learn in such a way so that it can fill this space. Yes or no? It could try to fill this space because I have not told anything to do. So better way to tell, or regularize this kind of feature to tell that no, whatever you are going to generate, you generate as as some place as a Gaussian. Why Gaussian? Because Gaussian, we know that very simple kind of function, na? Why Gaussian? Because we know that very simple kind of function, only two parameter mu and sigma, and we know that how to sample from that. Okay, so actually I have told you that how to solve this mystery. How to solve the mystery is to force, this is the original space, this is the autoencoder, this is the hidden space. I say from the hidden space, no, you cannot generate anything. You should generate only Gaussian. You should generate only Gaussian into this particular place. So how I can tell the Gaussian, I can ask this particular system to generate Gaussian. So apart from the reconstruction loss, reconstruction means whatever was the input, whatever the input, what is the output, they should be same. Apart from the reconstruction loss, I also tell them that whatever output you are going to generate, its distance with the Gaussian should be very small. Okay, and for that we can definitely use some kind of measure, because I can say that if you, instead of this, if you have generated this kind of future space, so this is not Gaussian, how can find out a difference? So there is a standard method called KL divergence. Okay, I can use any other method, such as any suitable kind of method we can use. So but we can use the KL divergence. We can say that the difference between this whatever you have generated and the standard normal should be very small. Okay, apart from this reconstruction loss, if I say that with both the two things I have to do, so definitely I know that the output is going to be Gaussian only. Okay, so so what I told you till now, that instead of using only reconstruction loss, which actually I was using earlier, that whatever is input, whatever output, they should be the same. I am also telling that there is one more loss, that is scale divergence, which is the difference between unit normal and the whatever you are going to generate, whatever my system is going to generate. This loss should also be small. Does it make any sense? Yes or no? So earlier I was telling that input and output should be same. This is the reconstruction loss. Input and output should be same. But I am telling that apart from this, do one more thing, that KL divergence between unit normal and the your hidden representation should be actually minimized. Is it clear? Can anybody write yes? If I do this, then definitely I have a lot of cat images I can supply over here. For every cat image, because different values are there. For every values, if for every bit, I can find out what is their mu. Mu is the mean only, na? What is their sigma? Mu and sigma we can find out for every bits for my database. So if I know that mu and sigma, yes, there is a question. Somebody raised hand. Please ask the question. Please type. Somebody raise the question. Any question, please? Hello, Neelam ji. I think you have raised the question. Hello. Hello,
Yes.
Dr. Neelam. Do you have any question?
See,
Dr. Neelam?
participants, if you have any question, then please type in the chat box, okay? So
Yes,
that
yes.
speaker can see in between and can answer accordingly.
I have a
Please
small
type
question.
question in the
Whether my
chat
screen is
box.
visible?
Yes, visible.
Okay. Okay, just give me a second. I think I have clicked on this and now I cannot see that what is. Just give me a second.
Can you write something so that we can see is it working or not?
I think I can hear you, Professor, but just now I cannot see. So you can see my screen. Okay, fine. This is
Yes.
okay. All right. So what I wanted to tell you, that if you apply these two kind of things over here, you apply these two kind of things over here, then two kind of features over there, then not only your input output is going to be the same, but your feature which are earlier which were actually wild, they actually become tamed, and they becomes normal, unit normal only. And if you know that, then if you know the unit normal, then you know that how can we do the sampling out of this, because you know that's how to do the sampling. I just wanted to tell you that because you know that Gaussian has a different probability of getting all the values, so we give you that what is the probability of getting this value, you pick all these values using some probability, you do a sampling, and by this you can generate a new vector, and then you can feed this vector over here and you can get the image of the new cat. You can think that this is a kind of manifold learning, and by this you can generate new kind of items over there. All right. So another approach could be that I just wanted to tell you another approach, and let's assume that I am going to make a autoencoder, okay, and it is only the second part, okay, that is the decoder part only. Here I say that if I supply 111, it should give me an image of cat. Is it possible that if I supply 111, it should generate an image of cat? Is it possible? You can say that how can it possible? So let me convince you in this way. Let's assume that I have a cat image, and when I supply this image, I am expecting that you should generate the image of this particular cat. So your system should your system should do, because your system should adjust the parameter. There are different parameters into this particular network. For any parameter, if you want to change this particular parameter, what should be the right value? So see that what is the output, what is the right now output, and what is this cat? What is the difference between these two images? And then you can find out what derivative with respect to this particular W, derivative with respect to the weight. You change this weight, then what would happen? This I would change to I dash so that it becomes very near to this particular cat image. You keep doing this thing multiple number of time. This image keeps changing and ultimately become cat image, because it's a gradient descent method. Ultimately, it is going to give you this answer. So with 111, you can generate a cat image. That is one thing. Okay. If I say that when I input 000, at that time show me a dog image, can you do this also? Again, you put 000 over here, keep a dog image over here, try to see the difference between these two items, change the parameter, and thus with 000 it would give the dog image, with 111 it would give the cat image. Okay, you can do the training. That's not a big thing. So if with the 000 it gives dog image, if 1111 it gives cat image, so what it would give you with this image, with this input? More clearly, with this input, what is the output you are going to expect? Cat or dog? Can you type? Cat or dog?
Sir, you are not audible.
I don't know why in between it gets muted. Okay. So what I was telling, that if this is a feature which is related to a person who was say 80 years old, this is a feature which is when the person was 70 years old, and we know that how the feature changes. So we can generate in between features also, and they actually correspond to the person who is actually when the person is into intermediate ages. Very interesting idea. Okay. Again, the same idea that I told you, that this is called the variational autoencoder. The idea is called the variational autoencoder. It says what? That for the given x, you find out what is mu and sigma. Okay. And then, because it's a trained model, it gives you mu and sigma. And from there, you do a sampling, create a new latent vector, supply it to the decoder. Decoder is going to give an image that is going to be the new image. Two kind of losses we have talked about. One is a reconstruction loss, another is a KL divergent loss. Now let me tell you something, some problems. So till now everything is okay. We are on a point where we can tell that we can generate new things. Okay, generative AI. Okay, this is called the generative AI. We can generate something. Everybody is okay that how can we generate new things? What is generative AI? How can we generate new things? Okay, respectively, we are actually talking in terms of the images. How can I generate images? Everybody is okay that how can we generate images? Can you please type yes or no? My audio is messing up. Okay. So everybody now understand that how to generate the images. Okay. Now I would try to tell you that what is the importance of adversarial training. Okay. And why it is required. Okay. To give you the background, I would like to bring your focus on these functions once again. What is reconstruction loss and what is scale divergence? Okay, one by one, and tell you that what is there, what issues there are, and how can we solve these issues using adversarial training. Okay. Till now we have understood that what is generative modeling. Okay. So reconstruction loss actually is the MSE, na? Mean square loss means for every pixel you try to see that what is the difference between the original pixel and the pixel that has been constructed, and you want to minimize this thing. So at the end, this, if this quantity is minimized, you are going to get the better images. Sir, what does KL divergence signify? Okay, KL divergence is actually difference between the two distributions. So this is the normal distribution, this is the distribution that I have. So if I want to reduce the KL divergence, means what? Both become same. If both become same, means what? This becomes normal, because I know that this is normal distribution. Na? So this also becomes normal distribution. Why I want normal distribution? Because for the normal distribution, only two parameters are there. And we know that how to do the sampling for them. Okay, so there is a question from Mini Priya ji. She is asking that generating new, whether it will work for the images only, whether we can generate new speech also. So the answer is that right now this is one shot generation. Na? Whatever you are going to give as a parameter, you are going to get output of that. So this is going to give you only one image. If you want to generate speech, means what? Multiple things which are actually there is a relationship, one sentence coming after this. So then you have to go to another architecture that is called RNN. Okay, RNN kind of architecture. So this architecture not generate speech. This would only generate only single thing. Or you know that the recent architecture such as uh, transformers, they are also going to generate at the same time a big sentence they can generate for you. Does it answer your question, Manipriya? Just type yes or no. Okay. So I wanted to tell you here that two different kind of loss functions we are going to consider. One is reconstruction loss, another is scale divergence. Let me tell you that what they are. So first, let me talk about the mean square MSE loss. Okay. So MSE loss is this, that for term by term you are going to find out the difference. Okay. Now let me ask a question. Assume these images A, B, C, D, E, and F. Okay. This is the image that you actually wanted to generate. Okay. If you generate, but you are not able to generate this image and you generate B image, is it fine? Instead of A, you generated B. Is it fine? Tell me. Yes or no? Just type yes. Okay. No. So is there a big difference between, you are telling no. So is there a big difference between A and B? Why you are telling no? Hmm? No big difference, na? So it is fine. Okay, na? It is okay that if I generate B image. Yes, it is fine. Is it fine? Okay. If I get, instead of this, if I generate C image, is there a difference between B and C? Please type. Not much, sir. But do you see difference? Any difference that you find out? Hmm? All are Einstein, no difference. Some color difference. Okay. So I think you can find out that looks like that this is more bright. Okay. C image is more bright than the B. Yes or no? C is more bright. Okay. More bright. If I somehow generate D image, is it good? Yes. There are some problem. Can you see that here there is some some white dot. Similarly, here there are some black dot. Here also you can find out some dots. It is called the salt and pepper noise. Okay. So D has a salt and pepper noise. So D is not that good image. Okay. Because there is salt and pepper noise. What about E? No, because there is a blur. Okay. There is a blur in this particular image. What about F? Here you can see some pixelation. You can see that checkerboard effect, some pixelation. You can see that some bad things are happening. Again, it is not good. Okay. F is pixelated. Okay. So if I want to find out that what is the difference between A minus B in terms of this value, okay, mean square error. Okay, what should be the mean square error? Okay, so can you help me to find out difference of the C, D, E, and F? What should be the value? If I say that, for example, A and B, the difference is 100 only. What should be the difference between A and C? Just write any number, not so big thing. Hmm? What should be 30? No, it is bright. Achha, 30 hai. It is, but if it is bright, then again it becomes difference. Na, there would be difference, huge difference. Okay, so let me say 30. Okay, what is the difference between A and D? Somebody is telling 150. I say 130. What is difference A and D? D is not good. Why? There was black and pepper noise. What is the difference between A and D? Please type how much it should be. Just write any number, no problem. 200. Okay. What is difference between A and E? This, where there is blur. 300. Okay. What is difference between this and F, where there is a pixelation effect? 350. Okay. Looks like that they are bad. Okay. And this image is good. Other images are bad. But actually, let me tell you that all of these images have the same MSE. So why I'm telling it? I'm telling it because you are trying to minimize this reconstruction loss. So what is going to happen, that you were expecting this image, but your system is going to generate this or this, anything it can generate. So it looks like that it is not a good idea. Okay, this is one problem. This is one problem with the reconstruction loss. Okay, and that's why the images would not be good. Do you understand this part? Second thing I wanted to tell you is the KL divergence. Okay, this this KL divergence part. KL divergence says that two distributions should be similar. Okay, so we can take it forward and backward. I think we should not go into that much detail, but I think you can just try to understand this part. Let's assume that your data is of this kind. Okay, your data is of this kind. Let's assume that you have a data of cat images and your distribution is of this kind. Okay, so if you want to fit a Gaussian on this, okay, so how can you fit the Gaussian? Gaussian would be something like this. How can you fit that? Hmm? You can put it here. Okay, you can make it smaller or bigger. Okay, or you can put it here. You can make it smaller, or you can make it bigger and put it somewhere here. So that it covers complete things. Okay, so I think because Gaussian is Gaussian, how can you fit in this way? Okay, so do you see any problem in this kind of fitting? Let me tell you what I wanted to say you. Right now, let me first try to understand that what is the problem with the right current setting. Okay, so currently, if I sample, because I have fitted it here, so I would take the data from this particular curve, because now this curve is not known to me now. This original curve is not known to me. This is only known to me because I have actually make it very clear near to that. So most of the item would be here, and they actually correspond to this particular place. They correspond to this particular place, and you see that this means what? In with me, this is was a high probability. This was a high probability area. Means looks like that these kinds of cats are very high. These kinds of cats are very high, but these kinds of cat are very rare. But because of my Gaussian fitting, this thing becomes this much. Means most of the time only this kind of image is going to be generated. So do you see that this is the right thing? Because these kind of cats are very less, but I'm only generating those kind of cats. Instead, if I make it smaller and maybe move it here, it could be a better idea. Okay, then what would happen? That I would not be able to generate these items. I would mostly generating only these items. Means one kind of cat I would be generating most of the time. These cats would not be generated. Are you able to see that? Yes or no? Can you please type yes? There are three cases. The one case when I am going to fit it here. Another case when I put it here. Third case when I put it in between. When I put it in between, the problem is items which are not there, they are getting generated. When I put it here, only these kind of cats images are going to be generated. These kind of cat images are not going to be generated. Similarly, you can think that if I put it here, put it here, then what would happen? Only this kind of cat image would be generated. This would not be generated because very high probability of, because with this very high probability is this particular value. So this kind of image is going to be generated. Is this global minima and global maximum points are? No. I'm just giving an example where let's assume that this is what your uh, this is what your actual distribution of the features are. But since I have actually asked to minimize the KL divergence between unit normal, so this signal cannot be captured this time, because this signal should have to be a normal Gaussian function only. So if I make it a Gaussian, so either it would be going from between or here or here. If it go here, then it would be generating things which are actually very less. If it is here, it is not going to generate these items, only these items going to generate it. This is what the problem is. Okay. Any questions? So this is the two problems when actually we actually specify that. However, if I don't specify these things, I cannot do the generation. So this is what the problem is. The big problem. Okay. Okay. So there is another point that sometimes people actually, instead of KL divergence, they actually use the JS divergence. So that is not a big thing to know. JS divergence is again a similar kind of thing. So to improve this particular idea, we are going to introduce one more thing. Earlier we were using this architecture. Okay, this was encoder decoder network, autoencoder that we were calling. This encoder part I am going to put here. This decoder part I am going to put here. This is a new architecture. Here decoder has given a new name called generator. Encoder is given a new name called discriminator. And this is a starting of GAN, Generative Adversarial Network. Once again, from the same kind of setting, from same setting, encoder is actually placed after, decoder is placed first, its name is changed to generator, and encoder becomes discriminator. Now in between there is an image generation. So the idea is that I feel noise to this generator, anything I feel, okay, noise, and whatever you feed, ultimately you are going to get an output. So let's assume that you get an image, and then I feed it with discriminator and ask that looks, tell me that whether it is a right image or wrong image. What do I mean by right and wrong? Let's assume that I wanted to generate a cat image. So if this is a cat image, I say that it is right image, otherwise wrong image. So I say 1, otherwise 0. Make sense? Okay. So this is called the specialized network called the Generative Adversarial Network. It is the name of this particular network, where this generator part is here. Okay, we feed it noise, as I told you that we feed it noise and it generates some image. is going to generate me an image. And because it is generated from noise, I can say that this is a fake, something fake has been generated. Okay. This is discriminator, which is actually shown the actual images. Actual images means actual cat images. I wanted to generate a cat image, so I show him the actual cat images, and then I show him both the images and ask him that can you discriminate? Can you tell me that which images are the cat or which images are not of the cat? Because I have not trained it anything. I don't know what is going to be generated over here. So whether discriminator would be able to do that? Most probably no. So I am going to build a system, and the system is this that from the database where cat images are there, let's assume 100 cat images are there, I take 50 cat images, 50 cat images. So I put 50 cat images, 1, 2, 3, 4, 5, 6, 7 cat images. And from the generator, I ask that can you give me 50 images? Generator also give me 50 images. So what should be label? I put these images because they are cat images, but they are generated from the fake images. So I say that they are fake images. This is a new database. Okay, this is the new database. I supply it to the discriminator for learning. I tell him that learn that these images are correct and these images are wrong. These are the correct images. These are the wrong images. I definitely permitted them so that their order is not like that only. Discriminator learn this that these are the cat images and these are the not cat images. Okay. So I provide this feedback to generator that now you are wrong. All your images are actually caught. So what the generator would do? It would change its parameter. How? That is a hidden part. It changes its parameter that because all these images are actually caught, changes its parameter and generate another set of 50 images. Again, I get training with them, and those images are again got caught. So it keeps generating those images. Okay. After some time, when the training is complete, I fix it. I say that okay, you are now discriminator. You take these images and you understand that what are the cat images and these are the fake images generated. It try to generate such that its image is also going to be called one by the discriminator. So after some time, this generator start generating cat images. Okay, because it wanted to be correct. It is going to change its parameter in such a way so that it can generate cat images. Very important part is this that I have not told anything to the cat, this generator to how the cat images looks. So the representation that this particular model has is now not restricted to the Gaussian only. This is the important part. Any questions on that? Any questions on that? This is the final point that I wanted to tell you. That was very important point. That since I have not told anything to the generator how cat images are looks like, I have never shown any cat image to generator. I have not asked the generator to minimize the Gaussian or any kind of specific function for generating the cat images. So that's why it is not restricted to be Gaussian only. This time it could be very general. And in fact, that general which actually represent the cat image actual space. And that's why it would be generating better images. Okay. So if you want to see this in terms of the probability, you can think that noise side supplied to the generator. Generator generates something. Cat images are of this kind. I take some images from the generated images and actual images, train the discriminator, provide the feedback that your images are wrong. It try to change this particular thing here and here and here, and after that it because it is changing, or sometime if there is any overlap between this and this, these images becomes correct. So try to shift itself so that it becomes this. Generator's hidden representation becomes correct. Okay. So how can we formulate this? Recall the cross entropy function. What is given and what is produced. If I want y and I produce y dash, the loss is y log y minus 1 minus y log 1 minus y bar. Okay. So this way we can define this time that this is what the loss is. Okay. Any questions on that? Okay. There is a question using back propagation. What does cat actual space means? Okay. So if there is a cat image, it could be 10 cross 10 image means 100 values. If I take it to the hidden space, in the hidden space, I can say that my vector is of size 30 only. My vector is of size 30 only. Okay. So this 30 would be how this is distributed for the actual cat images. Let's assume that this is where the cat images, actual images are distributed. But generator don't know it. So it may be generating something here. But after some time, it may get some images from here. They becomes correct. And then it try to change itself so that it also becomes the this particular area. This is the meaning of actual space. Are you able to understand this? This is the actual space where the 30-dimensional vector resides, hidden vector resides. Am I able to answer your question? Okay. Okay. So discriminative loss is defined in this way that y log y hat 1 minus y log 1 minus y hat. Try to understand this part that I am going to see with respect to okay. I think I was again automatically got muted. No problem. I will
Yeah.
repeat once again. Okay. So what I wanted to tell you that with respect to
Sir, you
Mittal
are
and
on
lies.
mute again.
Yeah, somebody I think is muting me. Okay, no problem. So let's assume that let me think with respect to the discriminator. Okay. If X that is being fed to it is a right image, if cat image is being fed, so it is a right image 1. If discriminator says 1 means okay, so there is no loss. But if says 1 instead of 1, if it says 0, so there is a loss. How much it should be loss? Hmm? If says 0, it should be very high loss. 0, the value should be very high. At the 1, it is 0. Okay. 0 should be very high value. Can you give me any function which is very high at the which is 0 at the 1? Here it is 0. At the 0 it is very high. Can you give me any function? So you know that log function, na? Log function is of this kind. Log. If I say that minus of log, minus negative log becomes this. And I am going to see the things between 0 and 1 only. So negative of log is a function which actually gives when dx is equal to 1, then it becomes 0. And when it becomes 1, when it is, let me type in this way, that if when it is 0, then it is a very high value loss. So that's why it is minus log dx. Similarly, when I feed an image generated from gx, so it is a wrong image because generator has generated it. But if discriminator says 1, it's a big bad thing because the discriminator has done an error because it should not say 1. So then it becomes minus log of 1 minus dgx. Okay. And if discriminator says 0, it's fine. Okay. There is no loss. So total loss becomes what? Minus of log dx minus of log 1 minus d gz of x. I should minimize this quantity. If you want to minimize this quantity, I remove the negative log, negative values, and we can say that I want to maximize this quantity. Okay. So objective of discriminator is to maximize this particular quantity. Okay. And generator actually since he wanted to fool this discriminator, it's actually instead of maximization, I say that it is minimization. So in combine, I can say that it is a min-max problem. And so I can say that generator is actually minimizing, and it is and for the discriminator, it is maximizing this particular quantity. This is what the equation is. And this is the equation actually gives you that actually is the main equation for the GAN, and gives you the flexibility that without specifying the parameters, the underlying uh, distribution into the generator, it can generate the very good kind of images. And that's why the images generated by the GAN kind of setting is actually very good. I would bring your attention to a GAN based paper, DC GAN, which was very popular paper, and very simple architecture. And you can see that these are the images generated by the GANs. They are very complex, but it's still very realistic. Some of the interesting ideas that has been seen on the GAN is this. Here you can see that these images, there are some ladies who are actually smiling, and then there are ladies which are not smiling, neutral faces. So if I subtract, let's assume that I know that what is the hidden representation of these images, what is the hidden representation of these images, and if I find out the difference between these two images, so what would be the difference? The smile. If I add that difference to any neutral man, it would become that the neutral man is actually smiling. Okay, this idea is called the walking into the latent space. Again, this is a very interesting piece of work that around 2014, this image was actually generated by GAN and was sold on very high price. You can see that. Similar, you can see that these are again the artworks. If you are a artistic person, you can appreciate these things. Okay. Then becomes a conditional GAN. Then that actually try to find out that what the descriptions of sub images. Then comes the pix to pix. Again, another implementation of the same thing where one kind of image is given and you generate a different kind of corresponding image. Map this Google direct images can be, satellite images can be converted to the map. Daytime images can be converted to nighttime images. This is a sketch. From the sketch you can generate that what is how the bag looks like. Different kind of colors and styles you can generate. And let's assume that this bag is even not prepared, but you are going to show this to your customers. If they like it, then they can order it, and now you can start producing it. So you are getting the idea before actually the production, because you're getting the order before your any kind of productions. This is another paper that is called the cycle gain, and cycle gain actually very fast paper that actually you can see that these are the zebras, they are converted to horses. Similarly, horses can be converted to zebras. Monet to photos, photos to monet. So you can see that a lot of style changes is possible very fast. Okay. This is another very interesting piece of work where images of the few peoples are actually shown. Can you guess that which are the people who are actually never existed on the earth? Can you guess which one is the, let me say that 1, 2, and 3. Can you tell which one is the person who has never existed on the earth?
Third
So
person.
the answer is, huh?
Third person.
You can type 1, 2, 3. 2, second one. This is wrong. Okay. It looks like that according to you, 1 is correct. Somebody is telling third means for him 2 is correct. Actually, all of them. Okay. So very realistic kind of images can be generated by this. Why it is happening? Again, I am telling that earlier we were using the Gaussian based fitting that has a serious problems that it was not able to generalize with respect to the underlying distribution. But GAN can adopt based on the distributions, and that's why they are going to be very good. And this is the importance of the adversarial kind of training. You are not going to show, but still they are going to show that. Another style GAN paper you can see on this, which actually says that these are the people A, these are the people B, and if we can mix the style of these two peoples, what is going to be made? For example, with this, if I make this boy, it looks like this. You can see that this particular area, which actually highlight the all kind of mixing of the different kind of features to us. So very interesting piece of work. With this, thank you very much for your attention. Hope you have tried to understand some part. And in case of your any questions, you can ask me anytime. For the PPT, if you wanted to download, you can immediately download it from here. KTIWARI.in. This is my website /talk/ppt-01.ppt. So if you wish, you can immediately download the PPT and read it from there. Thank you very much. Please ask any question if you have.
It's a kind request to all participants. Those who want to ask the question to the speaker, kindly raise your hand or either write in the chat box.
So no question from the participants. I think there is no raise hand and nothing on the chat box. Sir, kindly share mail ID. Okay, mail ID is available. You can search over that, and Dr. Kamlesh Tiwari has shared the complete home page. You can get everything from there.
If you want to download the PPT, you can download it immediately from this particular link. Thank you very much for being wonderful audience, and it was really a
So one
Wonderful.
question is there, Kamlesh sir.
Yeah,
What
please.
role do GAN play in the digital twin technology used in Industry 4.0?
Oh, there are a lot of applications are there. Okay. For example, look, in the digital twin, you wanted to generate something related to the same person. Na? For example, his avatar, etc. So it is very much required over there. Okay. So it has a huge applications. Try to see. It's a huge applications. Style transfer. I already told you that style transfer is one thing. So you can immediately use that. And one more thing is this, that these generations are very fast. So if speed is also very much required. So something is happening at slow space into the digital twin would not be that much appreciable. So again, these technologies are going to be used over there. All
So
right.
I
Any more
hope
questions?
no further questions. Okay, so if
Thank
you
you
have
very much.
any questions, then you can contact to Dr. Kamlesh Tiwari directly through the mail or whatever means.
Uh, sir, there is one question from Mahalakshmi. Role of GAN in text processing, especially in similar phrase, how it responds.
So look, text processing and all these things, GANs are not that much efficient. Why? Because attention is very much needed. So in those cases, we go for uh, attention based mechanism, what we call it these days, transformers. So look, because every next thing is going to be related to the previous thing, and GANs actually using noise produces one things in one go. Okay. So it is more to go towards the transformer than the GAN. Okay. Have I answered your question? Yes.
Thank you, sir.
Okay. Okay.
Okay, Sanjana, so conclude the session.
Tha- Thank you to Dr. Kamlesh Tiwari for an incredible, insightful session on adversarial training for generative models. Your detailed breakdown of adversarial techniques and their impact on improving model robustness was extremely valuable. Your expertise has certainly helped us gain a deeper understanding of how to build more resilient AI system. We truly appreciate your time and efforts. Thank you once again, sir. Next, we are excited to welcome our second keynote speaker of the day, Dr. Namita Mittal.
Sanjana, 1 minute, 1 minute. Dr. Kamlesh Tiwari, thank you for your nice session. And also thank you for accepting our invitation for taking this session.
Thank you very much for this
And
opportunity.
participants have well enjoyed your session very much. I can see the feedback also from the chat box. Okay, thank you very much, Kamlesh Tiwari.
Thank you. I'm leaving. Thank you.
Good evening, madam.
Good evening.
Sanjana, please start.
We are excited to welcome our second keynote speaker for the day, Dr. Namita Mittal. They will be discussing nut and bolt of transformer. Dr. Namita Mittal is an associate professor and the head of the Department of Computer Science and Engineering at Malvi National Institute of Technology, MNIT Jaipur. She earned her PhD in computer science and MTech in data science and engineering with over 25 years of teaching and research experience. Dr. Namita Mittal's expertise span over information retrieval, data mining, natural language processing, machine learning, data science, and generative AI. She has published 26 journal articles, 71 conference proceedings, and 3 book chapters, accumulating over 1,236 citations with an H index of 16. Dr. Namita Mittal is a recipient of Career Award for Young Teacher from AICTE, Government of India in 2004. She is also a senior member of IEEE since 2015. At MNIT Jaipur, Dr. Namita Mittal leads the Department of Computer Science and Engineering, contributing significantly to academic leadership and research advancement. She also serves as a coordinator for the subject expert group under the Unnat Bharat Abhiyan initiative. Now I would request to Dr. Namita Mittal kindly take over the stage and give them her a big round of applause.
Okay, madam.
Thank you. Thank you,
You can
Sanjita.
initiate. Participant, please mute yourself. Whenever you unmute, lot of noise are coming from your side. Please mute yourself. Don't unmute until you want to ask any question. Okay, please. It is the request. Madam, please start your
Yeah,
session.
yeah.
Your
Thank you
slide is
very much,
visible.
Sanjita, and thank you, Dr. Anurag, for inviting me for such a wonderful session. And I can see there are around 450, 459 participants at this time. It's really amazing to know that people are very keen to understand the concepts of generative AI. So today, because Dr. Kamlesh Tiwari has already taken a very good session, so in sequence of that, I'll continue with the transformer. So as you know, that what we mean by neural network architecture, we have some input, then some hidden layers, maybe one or many, and then we have some output to have the non-linear functions, right? So something with reference to the machine learning, that when we have the input and output, the AI makes, or neural network makes a function that may be a very complicated to satisfy our input as well as the output, right? So with reference to that, we have seen many architectures like RNN, CNN. In 2017, the transformer came up, that is nothing but the conversion from this to this place with the self-attention. So what is this? It's a type of neural network architecture that's specifically designed to handle sequence to sequence generation tasks. Basically, it came for the machine translation. Later, it has been used for the NLP mainly, and computer vision and speech recognition. So what are the advantage of transformer? Transformers use self-attention to process entire sequences in parallel. So far, we have seen the same kind of generation, but it was in a serial one, not parallel. It means it reduces the time complexity. Of course, when something is being done, eight persons are working together for a same task to be done, while one will do, then second will come, that he or she will do, and then third. Instead of that, eight persons are working for the same task, it would obviously it would be faster. So same thing is happening here. Transformer takes many sequences, that too in parallel. So advantage of this is parallel processing. The same advantage, we have the parallel computing. A long range dependency. Nowadays, because we are living in the era of the data, so many data, and the data is to be passed or to be considered. So long range dependencies. Somehow in the previous models, what happened? They were also considering the dependencies context from the previous one. But the question is how long it can go. So in the transformer, it is possible that we can go for the long range dependencies. Interpretable attention, the transformers can show which part of the sequence are important for prediction. So it's not like that it has everything in terms of the strength. It has some challenges also. These are the, of course, whatever we do, it has to have some, we have to pay some cost that comes in terms of the computational cost. So transformers can be computationally expensive. It means we have to have some good infrastructure and require a lot of time or data, of course, data for the training. Once it is trained perfectly, then it's no issue. It works well. So the birth of transformers, when it happened in 2017, everyone must have gone through this paper, Vaswani et al. Actually it is a kind of a main thing when it happened. Transformers arrived and reached. The team is from the Google Brain and Research. So introduce the transformer model, and it is, the name of the paper is Attention is All You Need. So what are the advancement? Why do we need it? What was the need for doing it? It eliminated the limitations of RNN and CNN, basically the context dependency, and introduced the self-attention. It means it understands the context from every word to every word in the document. That is a kind of amazing thing, that it has so much of computation power that it understands what is the connection with one word with the other word. Enabled parallel processing, leading to faster training and improved efficiency. These are the advancements needed, and transformers overcome this thing. So in terms of NLP, I'm taking this lecture in terms of NLP because I'll be taking the Python code to make it simpler, because everyone has to somehow understand through the coding. They can tune their program. And I'll take the simple examples to understand the transformer. So I have chosen, because I'm working in NLP, so I have chosen the example of NLP. So achieved state-of-the-art results in the language task in terms of the NLP, became the foundation for models like BERT and GPT. BERT is nothing but an encoder as a transformer, only encoder, and GPT is only decoder. While in terms of transformer, there may be many encoders and decoders. So in the terms of machine translation, text generation, sentiment analysis also, and the speech recognition also, it's working very well. So let's take a question. So far from the other classes, previous classes you have done, which of the following statements best characterized large language models in the context of NLP? You can write in the chat if you know the answer. Otherwise, I'll let you know the answer, because these questions are related with the this class kind of. So yes. So answer is yes.
जाऊंगी नहीं करके
So answer is D. LLM utilize transformer-based architectures with billions of parameters. That is the beauty. That's at a time we can, the billions of parameters have been trained, and these are the pre-trained on diverse and extensive textual data sets. So that's why it works perfect. Everyone is using nowadays LLM somehow, and it's giving good results. The second question, what is the primary component of a transformer architecture that allows it to handle sequential data without using recurrent networks? So answer is obvious. It has an attention mechanism. I hope everyone is agreeing. The next question, because I understand or I assume that you know RNN. Which of the following is a key advantage of transformers over RNN? Anyone? It handles the long range dependencies. Earlier, RNN also handling, but it handles long range dependency. Context is window size is bigger. So now the rise of the transformer happened in 2017, as we mentioned earlier. This was the paper. I have you can download it easily. It's free and open. So they introduced the original transformer model. That is a new paradigm in terms of the NLP. So what is the things or architecture in this model? They introduced, Vaswani and all introduced, that was it has encoder 6 layers for the processing of the input sequence. So now the question may arise, why 6 or why not many, or why not only 1? So 1 is not enough to handle the sequences because it has a long range dependencies. And similarly, we have the why not more than 6? They have limited it to 6, but because we keep on doing it, no issues, but it increases the complexity. And 6 layers were good enough to give the optimized results. Similarly, we have the decoders generates target output. So in the case of encoder and decoder, Encoder, it means some word embedding is to be done, and the decoder takes the word embedding generated by the encoder and it processes it. It gives the output what we want. So what was a major shift in this transformer architecture? We don't use RNN, LSTM, long short-term memory, CNN, convolution neural networks. Those all are replaced with the attention mechanism. Here we are assuming that you understand all these terms. So looking at this diagram, you can see we have inputs, then input embedding, and I hope my pen is working. Is highlighter. Yeah. So this is my input embedding, and here we have some encoders in the Apart from that, there's a new thing that you can see in the architecture, that is a positional encoding. This positional encoding has changed the scenario. So instead of only having the input embeddings, we are adding here, this is a plus sign, that is nothing but a concatenation. Concatenation is a kind of adding at the end. For example, I have got two strings, kel plus kel and keta. So kel and keta, if we concatenate it, it becomes kel keta, right? Similarly, put the encodings, it considers at what sequence, at what index the number is. We'll see with the simple example. Then after the result of input encoding, there are so many things to be done here. Feed forward and everything is to be normalized. Whatever we do, it may not be in the same range we want. So that is to be normalized. And normalized, we can have that this is the beginning and this is the end. Within this, it should come. This is a normal fundamental of normalization in data science. So similarly, the result of this encoder input embedding goes to the decoder, and decoder again process it, and then we have the softmax function at the end, and we find everything, whatever we get. So suppose we have a model of 512, then we are going to have probability against every line, right? And then best probability or highest probability will be considered. So this is what we have to understand today, one by one. So attention replaces recurrence. So recurrence is first recurrence. It means the previous answer is a part of the next sequence, and the next sequence answer becomes a input for the next sequence. Got it? So if we have PT is equal to PT minus 1 plus something. Similarly, if we have PT minus 1, it means PT minus 2 plus something. So that is kind of a recurrence. So attention replaces recurrence. So what is this? Why there's a need of replacement? Because RNN requires more operations as word distance increases. Look at this. Look at this sentence. The cat sat on the mat. This is the sentence. Now we have to find the connection between each word with each word. Look at this cat word. It has a relation with the cat, the cat to cat also, cat to set, cat to on, cat the, cat mat. Everything is to be connected. You must be wondering that how complex it would be. Yes, of course it is complex, but because we have the parallel processing, so it works well in terms of the time, in terms of the computational time complexity. So each word is compared to all other words, including itself. Like cat is connected with the cat. Computes dot products between word vectors and determine relationship. What is this? Cat is related with the cat. What is the relationship between these two? Of course, cat is same as cat, so it has a similarity. You must have gone through the cosine similarity. We'll be using it, cosine similarity. So example is the cat sat on the mat. Attention identifies key relationship. There's some relation with cat and set, relation with mat and on, and cat and cat. Cat and cat relationship is known as a self-reference, and cat and set. Cat is an object or a noun, and set is kind of a action. So we have a subject action link. Similarly, mat is object and on is a location context. On says is kind of a location. So these are the three relationship we found from this small sentence: the subject action link, location context link, and self-reference. This is just an example. We can have many more. So not only the single attention we can have, self-attention, we can have multi-head attention. So kind of a positional, looking at the back slide, we have how many kind of attention. It's a self-reference, it's a self-attention. While this is a subject action and this is a location. Similarly, we have a positional attention. At what position and how they are related. So multi-head attention we'll discuss with the Python code as well. The key features of multi-head attention, it means parallel attention mechanism. It runs 8 attention mechanism in parallel. We can't do it in serial because it is going to take much time then. So instead of working in serial sequence, we'll do it in a 8 attention. Looking back at the last slide, previous slide, we have got 3 attentions here. So if we can do it in parallel, three attentions can work parallelly. That becomes your multi-head attention. So what are the benefits of doing this? Allows deeper insights into sequences, no recurrence, eliminates sequential dependency, speeding up calculation. It means we don't have to worry what has been done in the past because the next attention is being taken into consideration and they all are working parallelly. And of course, parallelization always reduces training time and multiple perspective is coming from. So we have to look at the 360 degree angle. So what is the perspective? The cat sat on the mat. There may be many perspective. Got it? There may be some relation between cat and sat and mat and sat and cat and mat. So what there may be different perspective, right? So from the different perspective, we have to look at the context of each word. Got it? The cat sat on the mat. It was very tired. So what its significance? What it signifies? The it word signifies is about the cat or about the mat. Because human beings are the intelligent, we can say it always because it's related with the tired. So mat cannot be tired. So it should be cat only. But machine has to understand it. It means it's about the mat or it's about the cat or it's about something else. That is kind of a perspective. So in the Vaswani's paper, they mentioned encoder stack in the transformer one by one. So the original transformer model uses 6 identical layers. 1 is not enough, 2 is not enough, 3 is not enough. So ultimately researchers concluded that 6 is good enough to work with. So each layer consists of 2 main sublayers, multi-headed attention mechanism, and fully connected position-wise feed-forward network. There are 2 sublayers in the one encoder. So it means every encoder will have these 2 sublayers. Got it? So what are the key points behind it? It captures multiple relationship within the sequence. Multi-head attention is needed because we need to capture multiple relations within the sequence. Because it's not that simple that cat sat on a mat. We have the complicated sentence. There may be anaphor resolutions as well. We have to find it out. Then feed forward network, as we understand, feed forward is going ahead. Feed forward network process each position in the sequence independently. Let's take an example. So before we come to the Python code, there's one more term that is to be understood, that residual connections in the encoder. This is residual. Sorry, this is about the encoder. So here we have one. This is one sublayer and this is another sublayer. I hope my point is moving. There are 2 sublayers in one layer, and similarly we have 6 layers kind of thing. That is an encoder. So what is this residual about? This is each main sublayer in the transformer, that is multi-head attention and feed-forward network, is surrounded by a residual connection. So input X is added to the output of sublayer before passing through layer normalization. Normalization, as we understand, that something is to be fitted into the range. This is my begin, this is my end. It cannot go beyond that, right? So layer normalization is kind of X, that is my input. And what is the output of the sublayer? So we are not forgetting the input, basic input. We are again using it. Layers normalization is a function which takes X again, and the output we are getting from the sublayer X. So what is the purpose of doing this? It prevents the loss of important information. Anyhow, we don't want to lose the information. That is our target. So positional encoding, basically, at what position the word in the input, at what position the cat sat, the cat is coming at the second position. If we start from 0, is coming at this first position. That is a positional encoding. And what is the relation between cat and mat? What is the relation between cat and set? At what position they are coming? If we change the position, it means sometimes we lose the context or the different context we are reaching in, right? So that context is to be maintained. So what is the key insight from this one? This says the structure of each layer of the 6 encoder layers is identical. We have got 2 in each encoder layer. We have got 2 sublayers. But the content changes layer by layer. It's not exactly the same one layer is doing. One layer, the second layer is taking the input from the original X as well as the output of the first layer. Similarly, the third layer of encoder is taking the input, that is original X, plus the output of the second layer. Got it? So the embedding sublayer is only present in the first layer and ensuring stability in the encoding process. So same function across layer, multi-head attention works in each layer. Same function across layers, but each layer learns different association between tokens. So let's assume that the Vaswani and team has assumed that D model is equal to 512. It can be adjusted. So simple to work with 512. So ensures consistent dimensions across all sublayers. So every time we are getting the output, that is dimension of 512. Ultimately, we are reaching at 512 output. It includes the embeddings and residuals. And apart from that, we will be working on the positional embeddings and positional encodings. There are 2 terms, positional embedding and positional encoding. We'll see how do we derive it. So the key advantage of this one is reduces the number of operations, optimizing efficiency. This is what we are working for. Stable dimensions make it easier to track information flow. So if we see the global view of the encoder, it says the transformer encoder is highly optimized with efficient computation and stable flow of information. If you have any doubt, we'll try to understand in the Python code. So the purpose of input embedding converts input tokens. That is the purpose of embedding. That every text is to be converted into some digit. That is, every token, every sentence is converted into tokens first, and every token is converted into the vector of dimension, that is continuous, right? Word embedding. So here every token, the cat sat on the mat, that the will be converted into 512 vector of 512 dimension. It uses learned embeddings to represent the input in vector space. So here, look at the diagram. Here we have some input, and input is nothing but your text, and text is converted into tokenized into tokens, and every token will have some input embedding. So the embedding is a classical approach you must have gone through, where each token is mapped to a continuous vector. It is continuous, right? Some values are negative, some values are positive, some values are higher. Ultimately, we have to normalize it. So it ensures the input tokens are represented in a way that can be processed by the transformer model. So input embedding sublayer of the transformer is input are converted into tokens, and every token has an input embedding. In this model is 512 dimension. We can change. So taking a simple example, the embedding sublayer operates like other transaction models. It's nothing but the conversion. A tokenizer converts a sentence into discrete tokens that the model can process. For example, I have an input. The transformer is an innovative NLP model. Look at this exclamation mark at the end. So this will be tokenized into the. So look at this. The transformer is an innovative NLP and model. And here this is also anything, any punctuation mark, maybe comma or something. If it becomes the part of the sentence, that is to be considered. So I hope it's understood. This is sentence we have converted into the tokens. Now, every token will be having an embedding of 512 size. Every token will be having a vector of size 512. How it comes? They are again the word embedding models. Anyone we can use. One of them is very popular, word2vec. You can use anything. So tokenization and integer representation, how they are related? Generally, tokenizers often normalize text into lowercase. So look at this. The cat slept on the couch. So T is a capital here, while in the tokenize it became small. So everything is converted into small. And the integer representation, here you could see that the is coming at the first position, cat is coming in the second position, and so on. So look at this example. The is 1. The cat slept on the couch. It was too tired to get up. Right? The cat slept on the couch. It was too tired to get up. So as a human being, again, you can understand this is what we are resolving the context. It means cat, while it may be couch as well. Sorry. Just a second. So every text can have these tokens. Instead of 1, 2, 3, they may be different. 1996. If the is coming twice in the sentence, it will have the same thing. So look at this. Instead of 1, I have taken 1996. So 1996 is again coming here. This is representing your the. So the is 1996, cat is 4937, slept is 7771, on is 2006, on is something, and similarly is again coming the 1996. So every token has got some number. So for the simplicity, I have taken it discrete, and to make you understand, the repeated words are having the same token number. Got it? So this sentence is converted into the unique integer. Got it? So now we are ready for the embeddings. So here we can use word2vec embedding or any other embedding you would like to have. There are many. One of them is a script-gram model. So tokenized text must be embedded to provide meaningful vector representation. Here, look at this. So we must have some connection. The cat, 1996 and 4937, they must have some connection. Slapped is, the cat is a noun or an object, reference, and slapped is nothing but your subject, action. Sorry, cat is subject and slapped is the action. So they must have some connection in between. That is what word embedding is keeping it. So the transformer uses a learned embedding sublayer. Script-gram model predicts context words based on the center word. So here we have word I, and what it's saying before 2 words, that depends on the word window size. We keep on increasing, but as soon as we increase the window size, it increases the complexity. So this is word I plus 1, 2 size before and 2 size after. Structure, input layer receives tokenized word. Input layer receives tokenized word that we have seen the previous slide, and we have hidden layers. So it's not enough to have no hidden layer, input layer and output. That is what we have seen in the traditional language, traditional programming language. We pass something, we write our input code and get the, we pass the data and we get the output. But here, this is input. Input we know, output we know, and we have to train our model. If I say y is nothing but f of x is nothing but sequence of input, and y we are getting the output. So what is this f of x? Is nothing but a model. Is nothing but a model. So if I say, let me check it. Anyhow, so output, it generates word embeddings of the tokenized input in the case of embedding. In general, we need input to be passed and output to be received from the model. So input embedding is receiving the tokens and generating the embeddings. Got it? But in the case of decoder, that is a part of the encoder. And in the case of decoder, we get input as a output of the encoder, and output of the decoder would be the probability after softmax function, and the highest probability will be given the, in case of sequence to sequence generation. If I say the cat sat on the mat, the cat sat on and question mark, then mat will be generated using the self attention. That is the logic of the transformer. So now you are coming to the Python programming kind of thing. So you can start working in your collab if you have, then I'll share the code. The embedding example sentence, the black cat sat on the couch and the brown dog slept on the rug. This is the sentence. Now, our focus is black and brown. The black cat and the brown dog. Do they have some similarity? They have some connection, because the black cat sat on the couch and the brown dog slept on the rug. There are two different sentences. Still, we are trying to have some connection between the black and brown, cat and dog, and couch and rug. The word embedding for black and brown should be similar, since they represent similar concept in terms of the color, or adjective of a subject. So how do we find this similarity? So when each word is converted into a word embedding, and here we assume that our word embedding, one vector, is of 512 dimension. So black will be converted into word embedding. Look at this. Here I have taken, I assume that this is the embedding. This is full. From this to this. From this to this. This is nothing but everything about the black. These are 512 inputs. This represent black. Similarly, we have some representation about the brown. Right? This is the brown representation. Again, 512. It's not, in between, there's a 3 dots, right? It means it's continuation. You can see it from this one. This one. These are 3 dots. So in total, there are 512 the continuous data, and for brown. If we find the cosine similarity between these two, we know the cosine similarity. Cosine similarity is nothing but the Euclidean distance of L2 norm. Got it? So we have represented black and we have represented brown. Now, the original transformer, other embedding methods can be applied. The D model can be adjusted for different use cases for allowing for larger. Sometimes people use 1024 embeddings. Sometimes people use 64 embeddings. It depends on the logic. So now we have to find the similarity between black and brown. I hope now it's becoming simpler for you. So every word, here we have taken only 2 words and finding the similarity. Similarly, for every word has got some similarity with other. It depends on the embedding. So as you know, the cosine of any angle goes from 0 to 1. Got it? So kind of a normalization we are using. So angle between these two vectors right? So interpretation is the high similarity value is close to 0. It means the words black and brown are semantically similar in the embedding space. Whatever we have created is matching with our real life scenario because black and brown are the colors. That's how we are checking what we have done in terms of embedding is good enough or not. Similarly, if I say the cat and dog, if I find the word embeddings of both cat and dog and try to have the cosine similarity or any other kind of similarity, then they must be close because they are the animals. Similarly, we can have the person and the cat. Do they have some similarity? Or a human being or a monkey? Do we have some similarity? Got it? That is what we are finding it. So the role of positional encoding, now there are two terms, positional embedding and positional encoding, PC and PE. So skip-gram model has successfully learned that the black and brown are semantically related as indicated by their close embeddings. This semantically relationship allows the transformer to begin with the good associations between the words. Now, the still positional encoding has not yet come. Still, before that, positional information is absent in the learned embeddings. We have seen there was some brown, black cat and brown dog. But how they are distant, how near they are, how far they are in a sentence, how they are related position-wise. So looking at the sentence here, I'm coming back to the sentence. Yes, sorry. The black cat sat on the couch and the brown dog slept on the rug. So we need to find the position. The black is coming at the second position while brown is coming at 2, 3, 4, 5, 6, 7, 8, 9, 10 at 10th position. So that is what it means a lot. How far they are distant. That is what we are trying to get from the transformers. So position encoding with sine and cosine. So Vaswani and team reached to the conclusion that if we can add this position encoding in the positional embedding, how do we do it? With the use of sine and cosine. As we know, the sine and cosine functions, they get the input in terms of the angle and their range is always from 1 to -1. Got it? So we can have the position in the sequence words called black, that is the position 2, and brown at position 10 need position information added to their embedding. So we have seen the embedding of black, or similarly we have seen the embedding of brown. I'm coming back to previous slide where brown is this is the embedding of this. So somehow if we can add at the positions as well, how they are related 2 and 10. If I get the similarity between black and brown, we have seen that it's coming 0.9 something, right? It's very similar. But of course, we know that they are similar. If I write the black and brown are the colors. So black is at the second position, brown is at third position, very similar. But here the cat, that is a black, and the dog, that is a brown, they are having a different positions, 2 and 10. So somehow this similarity coming 0.96 should not be that one. It depends on the sentence. In the same sentence, in the different sentences, black and brown position matters a lot. That is what positional encoding is saying. So this is, yes, cosine similarity, black and brown is coming 0.999. So is similar to 1, is close to 1. Got it? So here, it is similarly saying yeah, thank you. So here the black cat sat on the couch and the brown dog slept on the rug. We have to find the distance. Got it? So designers, those are the researchers, used a clever method used based on the sine and cosine function. That is kind of a transformation game with the transformer. This approach ensures that the positional encoding values remain small and computationally efficient while still being informative. So I'll find the similarity with the use of cosine and sine. So they use this that is known as a positional encodings. There were positional embedding and positional encoding. So we'll use this new thing that is PE and PC. PC is nothing but your word embedding plus PE, positional encoding. The sine function is applied to even index. They smartly what they did to have the difference between the even and odd. For the even, they use the sine. For odds, they have used the cosine. For example, if I start from 0, that is considered as an even, then we use sine. And then next is 1. 1 is odd. For that, we use the cosine. So here 2i, because even on whenever we use even an odd concept, then we use 2i. So for even dimension, we use sine. P is nothing but your position. 10,000 raised to power 2i divided by d of model. This is for normalization. And the question is, why 10,000? Again, the researchers started with 100. If I say 100 raised to power 2i and I is 0, it becomes 100 raised to power 0. That is nothing but 1. If I say 2i, 1000, 1000 is 10 raised to power 2. 10 into 10, 100. 10 into 100 into 100, 1000, and so on. So 2i is nothing but I assume as sorry, I can't do it. So here, this is the formula they have derived. The 10,000 is sufficient. Beyond that also can go, but because it's coming in the numerator, it will decrease the value of the input function we are passing to sine and cosine. Got it? So somehow 10,000 is a perfect value for using it. So we can have the variations in positions from 0 to 255. And cosine for variations may exist in somehow implementations. Some people may take 0 to 255 sine and 256 to 511 was cosine. But the Vaswani and group made it like even and odd. So look at this. This is a Python code I was mentioning that this was the function. Here we have pass position, comma, pi. Position means p. So this is a function. Here, assume that we take the position index that is sits. The cat sits on mat. This is my sentence. The cat sits on mat. The third word is sits and index is 2 because index always starts from 0. So 0, 1, 2. Sits position is 2. Index position is 2. So how do we find the embedding, dimension embedding? PE is because it's coming at the 2 position is even. And 2, 0 for index, for dimension index 0, 1, 2 and everything I have to calculate for sets. Index I becomes 0, then 1, then 2 and so on. We have to do it because we need to find the embeddings of 5, 1, 2. For everything we have to calculate it. I'm calculating it for simplicity for the 0th index and first index and we'll add it. So here 2 remains same. 2 remains, this is the position of the sets. It will remain same. Now this 0 and this 0 is same. This 0 and this 0 is same. Here we are saying sine 2 is my position P divided by 10,000. 2 multiplied by 0. Index is 0 by 4. What was this 4? This is a, look at the formula. 2i divided by d model. D model ka square root. Square root is, here we are saying, you can change it for the simplicity. Here we are reaching the 2 divided by 10,000 raised to power 0, because everything we multiplied by 0 will become 0. This becomes sine 2. Similarly, for the next one, I is 1, second embedding. Similarly, we have third embedding, fourth embedding, 5 embedding, and it keeps on increasing index. It starts from 0 and goes up to 2, 5, 5, 1, 1, 5, 1, 1. So this is, here we are using the, for I in range 0 to 2, 5, 1, 2, and this is 2 by 2. 1, 1, this is 1 for the sine and other for the cosine, right? So match dot sine is position 10,000 raised to power, this is raised to power 2i divided by d model, and PE01 is a double match dot position divided by this d model, and it returns PE. Now the question is again, why 10,000? 10,000 is somehow is a trade-off between having the good performance with the low computation power. As we keep on increasing, because it's raised to power this, right? 10 raised to power this, 10 raised to power 1, 10 raised to power 2, 10 raised to power 3. So it's good to compute. So since 10,000 raised to power 0.5 is coming 100, and it simplifies to this one. So this is the embedding. This graph is showing the embedding of positional embedding. We have the word embedding that we have calculated, as you have seen in the example of brown and black. Similarly, for brown and black, we have to find the positional encoding, right? Positional encoding is nothing but PC is equal to PE plus word embedding. Got it? So now look at this same example we have taken. So this was PE. PE matlab E stands for the second position. In the one statement, the black cat sat on the couch and the brown dog slept on the rug. The word black, this is a second position. As at position 2, brown is at a position 10. Using the sine and cosine functions, we generate a positional encoding vector for black at position 2. The positional encoding ensures each word's unique position within the sequence is captured in a 512 dimensional vector. So earlier we had seen the word embedding of black. Now this is a new embedding of position of black. Similarly, we will have the positional embedding at position 10, that is brown. That is brown. Got it? So now how do we edit? Got it? Yeah. So this is cosine similarity for positions. Black at position 2. This is position embedding. And this. So cosine similarity, if you find position 2, that is your black, and this is your brown, and we find the cosine similarity between these two is coming 0.86. While earlier, you remember what happened? The word embedding, on the basis of word embeddings, this was coming 0.999 approximately. Now, which one is to be used? How do we use it? We are not happy with 0.86 and we are not happy with 0.99. We have to have a trade-off because, of course, we know that black and brown are colors very similar. But the question is, in this sentence, they are distant at different two places, not 2 and 3. They are 2 and 10. So somehow the new positional encoding that matters. There are two embeddings we have seen. Word embedding 0.999. I'm taking the same example so that you understand it well. And we have the positional embedding. Now we need to find positional encoding. So positional, look at the diagram. We have seen the X1, assume that this is black. This is token. X1 is black, X2 is brown. And we have done some embedding. Say in terms of Y, we have seen the 512 vector, 512 dimension vector. Here also we had vector. Similarly, we could find this one PE2, PE black, PE brown. Now we have to add them. Now it's not a concatenation, it's adding, because ultimately we need 512 vector only, 512 dimension vector only. So how do we add it? फर्स्ट वाला इसके फर्स्ट वाले में ऐड हो जाएगा, सेकंड वाला इसके सेकंड वाले में ऐड हो जाएगा. So one is mapped with one adding. If suppose this is 0.1, first position पे 0.1 है and is also 0.11. So this would be 0.21. So on. So this becomes your PC. We started with input, then we converted into word embedding. Similarly, we converted positional embedding for black, and then now we are adding. So it would be something different because here we have some values in minus. So it's not always that it would be scaled. Something would be negative, less negative, something may be more negative, because this may be negative, this may be negative. And everything is to be added for 512 dimension. This also, and we are reaching to this. Look at this. For example, black's word embedding, that is combined with its positional encoding PE2 to obtain PC black. The PC black is a token is equal to Y1, that is a word embedding, and PE2 PE black, that is your positional embedding, positional vector. And ultimately what we get is positional encoding. Now we have to find the cosine similarity of two words with reference to the positional encoding. So multiply the word embedding Y1.
சித்தி இருக்காங்க, எல்லாரும் இருக்காங்க. அப்புறம் எப்படி ஹார்ட் அட்டாக் வரும்? ஏன் ஹார்ட் அட்டாக் வருது? நெஞ்சு வலியா?
Kindly mute yourself.
குத்துதா?
So now we have to multiply the word embedding vector that we have retrieved from the word embedding by math.square root, because we have to normalize it. D model, that is nothing but a dimension of the model. Here we have fixed 512 to preserve its information. So Y1 is a new Y1 becomes Y1 into Y1 divided by the D model. That is for kind of a normalization. You can do it or do not. This scaling ensures the word embedding contributes effectively without being overshadowed by the positional encoding. Got it? So we have the new Y1 and yes, I'll come to that. Final position encoding is Y1. We have already done new Y1 plus PE that we have just calculated for the black and brown. That has been added. So if I is nothing but your index, that was 2. So YI is word embedding and PE is a position embedding of word black, and we get the new embedding. So imagine that PC black has got this embedding. Again, 512 values. It's a vector. Similarly, this vector will be coming for the brown. This is brown. Now you find the similarity, cosine similarity. We have seen the similarity, cosine similarity with word embedding. It was coming 0.999. Then we came to positional encoding. That was 0.86. And now the new cosine similarity, new similarity, we are using again cosine similarity. Same we have to do. Now is coming 0.9627. So it's kind of a in between. Or yes, of course, black and brown are very similar because they are the adjectives used here, mentioning the color. But it's not 0.99. They are not that similar. It's close to 1. They are similar, near to 0.96. That is what it has been proposed in the transformer. So what is a new thing? Beyond the RNNC and other methods, that we have the positional encoding that has been added to the word embedding. So what is the effect of this positional encoding? Word embeddings are highly similar, we have seen. Positional encoding decreases similarity because positions are distant. But ultimately, we have to have the trade-off. We want the word embeddings as well as the positional embeddings. So it's reaching to the 0.9627. So this is about the 2 words in one sentence. What if we have everything is to be calculated, fully connected network we have. Everything is to connect, will be calculated with everyone. So it seems very computationally high, but because we do it in parallel, it seems it works well. So word embeddings plus positional embedding, adding positional encoding to the word embeddings results in this. Each word's position encoding now reflects both the semantic and the positional information. So practical, you can use Hugging Face and Google Brain Tracks. They offer libraries that simplifies this process. For those who are interested in the code, resources are available on GitHub and the collaborative notebook, because we need GPU for that. So it's good to use, instead of CPU, you can use GPU or TPU from the collab. I hope everyone is nowadays using the Python with the help of collaborative notebook. Now we'll come to the questions. Yes. So the second question, in the context of transformers, what does self-attention refers to? You can write in chat. Self-attention refers to the. So answer is each word attempting to every other word in the same sequence. No word is left. Got it? The second question is, what is the role of positional encoding in transformer model? The first option is to encode the position of the word in the sequence. Is it right? Yes. Because in the earlier models, it was missing. So if we have a paragraph or a document of 10 sentences, and first word is placed at the first index, and the second one, which we are comparing with, is at the last. So somehow they are not connected, because there may be some synonyms. Then again, we have to find the similarity between the words. Those are having the synonym words together. If I say Sachin Tendulkar is a Indian cricketer, he is very popular. So he mentions Sachin. So somehow Sachin and they are very far, not very far. They are related. Although it seems very far, in the second sentence is coming. It is known as an anaphora resolution in the NLP, but it indicates that it is Sachin and Sachin is not distant. Now, what happens in the case of, so far we have seen this. Now we'll be using this technique in our other layers. So what happens in the case of multi-head attention sublayer? This architecture is same from the same paper when transformer evolved. Multi-head attention in this paper contains 8 heads. From the different perspective, we are getting the semantics. So there are 8 perspectives. So every perspective will work in parallel and ultimately will add them. So as we have 5 1-2 dimensions, we can divide this 5 1-2 dimension for 8 heads, 8 attention into 5 1-2 divided by 8. That is 64. So first 64 is for first attention, and the next 64 is for next attention, next head, and so on. So this model allows model to focus on different parts of the input sequence. Input sequence is your sentence. So again, once it is normalized, everything is to be kept in a range. So after normalization, adds residuals, connections, and normalize the output. The architecture, the attention mechanism is designed to improve the model's ability. Why do we do it? To capture the various dependencies in the sequence. first word is connected with the second word, or first word is connected with the 7th word or 10th word, as you have seen in the second word and the 10th word is connected in similarity, that is what we have to look at. So in the case of input representation, each word in the sequence is represented, as we have seen, in the 5 and 2 dimensions. That is known as a D model, combining word embeddings and positional embeddings. So positional encoding becomes D1 is equal to this, D2 is equal to this, D5 and 2 is equal to this. You can see it's a big number. Now each word is mapped to all other words as well. This is all about the xth word. We can have so many words. So each word is mapped to all other words in the sequence. This is the people must, participants must be wondering what we keep in these 5, 1, 2. What they represent? They represent the relationship or semantics related with each other. So now coming back to the same example, the cat sat on the rug and it was dry cleaned. So here the question is, what does it mean by it? Is it a cat or a rug? As again, we are intelligent ones, that is what we want machine to be. It should be the cat should be dry cleaned, or the rug should be dry cleaned. If I say the cat sat on the rug and it was quite tired, so we can assume that rug cannot be tired, so it should be cat. But here the dry clean, there must be some connection between the cat and rug and the dry cleaned. So what is the challenge? Challenge is the one D model block would provide a single perspective. So far, we had only one single perspective. Now we have to think this perception from the 360-degree angle. It could be computationally expensive, but it works well because it works in parallel. And apart from that parallelism, parallelization, sorry, we have multi-head attention. So we cannot have lots of attention. We have to have again a trade-off. So in this paper, they have taken eight head attentions. So if our model is of 5 and 2 dimension, it's good to have 8 because every attention we work on the first 64 dimension. So efficient training with the multi-head attention, we have model is 5 and 2 and 8 heads, multi-head, each with the dimension 64. And they are working in parallel for faster training. So if we have one head connects it with the cat, the same example, the cat sat on the rug and it was dry cleaned. So the cat and it, how they are related. The another connect is it with the rug and another connect rug with the dry clean. So each head learns. Here, for simplicity, we have taken 3 heads. So as we have seen earlier as well, 3 heads, the cat sat on the mat. Cat is a self-reference, self-attention, and then action attention, and one more attention was there. Here also, the 5 and 2 model is divided into 8 heads. Every head has got 64 dimensions. And at the end, multi-headed, the output from these 8 heads will be concatenated. They will be adding at the end. This is how the multi-head attention works. So individual head output, each head produces a matrix, say ZR, with shape X into DX. X is nothing but your input. So the output of the multi-head attention layer is Z0 to 7. We start from 0, so it reaches to 7. So the matrices from each head are concatenated to produce the final output. The final output shape would be X, that is your head, and the D model, where D model is 5 and 2. So the concatenation ensures the output meets the original transformer model's dimensionality constraint. That was 512. Now, here they have introduced the concept of key value. Now, everything, why we do it? We do the training. We say this is a pre-trained model. It works well for the sentiment analysis. This works well for this one. That is kind of a fine tuning. We have got pre-trained model. Depending on the application, we can fine tune it. Now, the question is the cat set on the question mark. We have already pre-trained model. The cat sat on the rug and it was dirty and this and that. That has been trained. Now we are asking a question. The cat sat on the question mark. The answer must be rug or mat. Got it? So this is our query. Query is again into 64 vector dimension. Again word embedding. And the key is again 64, provides an attention score and value. If we look at the document, it has some meta words or document has some title. You can understand key is kind of a title. At this slide, we have attention mechanism in multi-head attention is kind of a key. And value is a detailed about the document. So whatever has been written on this slide, it becomes your V. Got it? So there's a formula that this attention, it needs Q, K, and V. We are working for the pre-trained model. And we assume that we have enough documents, those were pre-trained. Nothing new, nothing out of vocabulary. So whatever we get from this QKT, that is nothing but Q is a query. Key is your metaverse title of the document. If Q is your query, that is text, and K is your title of the document, dot product, K transpose, dot product, and divided by square root of dk, that is for normalization, and multiplied by V, and then softmax. As you know, softmax is getting your probabilities of all the dimension. Whatever we are going to receive, those are having the high attention, high values, will be having the higher probability. And got it? So first we have to do scaled dot product attention. I'll come to the calculation part, don't worry. Attention is computed using the equation this, and the purpose is it decides the relevance of each word in the relation to others. Relation means relationship between each other. And having the higher relationship means similarity higher will have the higher probability to come. So if we assume that there are three vectors, Q, K, V, and obtained by dot products between input X and their respective weights, if I say there are word A, B, C, yeah, Q1, Q2, Q3. Similarly, we have K1, K2, K3. They have some weights. And if the similar words are there in the query in the key, then they will have the weights and will be multiplied. As we do in the information retrieval, dot product, weights are multiplied. If some token or a key word is not available in the query, but that is available in the key, because it's not available in the query, it will have the weight 0, and 0 will be multiplied by the weight of the key. It will become 0. If the token or a word has got 5 weights in Q and 10 weights in K, will be multiplied by 50. 5 into 10, that is 50. This is higher value. This is how we calculate it. So weight matrix, again, we have dimension. We have 8 heads. So divided into 8. So it's reaching to 64. So output vector of everything, Q, K, V will be 64. Got it? That is our constraint. We have to, because we have to concatenate at the last. So dot product is kind of a Q and X in QW, that is nothing but your weight, resulting in Q having a dimension of dk is equal to 64. So we can adjust, not necessary that you take these parameters for your program. You can take as per your wish. But this is the simplest model to understand. So libraries are available in Hugging Face and Google Brain Tracks. It provides the frameworks, libraries. If you want to go into deep transformer architecture by implementing keys aspects in Python, it is available using the NumPy and a softmax function. I hope you understand softmax function to run and visualize this. So now we'll take one by one with the Python code. Right? I'm quite slow. You can do it parallelly, or if you don't want to do it right now, it's okay. You can do it later. So first we have to save in the collaboratory, input the setup in the Google Drive. Of course, we have to have a Google Drive, Google Gmail ID, and with that associated Google Drive, we can open it, Google Colab. The notebook is available in the GitHub, and begin with minimal Python functions to understand the transformer at a lower level. So we have to, because NumPy is a Python for the numbers as NP. And then SkyPy.special for the softmax function. These are the libraries we have to import from the available libraries. So first, what we are doing, we are making it a bit, we are lowering down. Instead of D model 64, we are making it for 4 instead of D model is 4 for simplicity instead of 5 and 2. So this simplifies the input vectors for easier understanding and visualization. So we have input contains 3 vectors and 4 dimensions. Our model is of 4 dimension. So first step, what we do, we input it. We have 3 vectors. Every vector will have the 4 dimension. So this is how we write our matrix in the Python. Got it? So X is the name of the matrix with this one. And input, it means one word. It has the embeddings of 4 because size is this. So first step of our model is ready. Now incorporating weight matrices into the model to transform the input vectors. This is input number 2, input number 3, input of multi-head attention sublayer. We have got 3 inputs and we are incorporating weight matrices. So here we have passed 1 0 1 1 1 0, sorry, and this is second one is 0 2 0 2 1 1 1 1. These were the 4 values, right? So this is same 1 0 1 0 1 0 1 0 0 2 0 2, and it is 1 1 1 1 1 1 1 1. These are the 3 matrices. Got it? Simple. Now we have weight matrices used to train the queries. KW used to train the Q. We have to have the key value mapping used to train the values. So to simplify the visualization, the matrices are scaled down to dk is equal to 3 and D model is equal to 4, as we have mentioned earlier. So that's why only 3 inputs and our embedding is of 4 size. So purpose, these matrices will be applied to the input vectors for the attention mechanism. So W query is the query weight matrix of size 4 by 3 W query, because we need to multiply as we have to multiply 2 matrices, we have to consider the number of columns of first matrix must be equal to the number of rows of second matrix. So that's why the W query that is to be multiplied should have the size of 4 by 3. Earlier it was 3 by 4, now it's 4 by 3, so that we can multiply. So W query assumed, we have assumed that 101 100, 001, 011. These are the weights, generated vectors that will interact with the key vectors in the attention mechanism. Now, how do we multiply it? We can multiply it by the matrix multiplication dot product. So W key is the key weight matrix of the size 4/3, and it transforms input vectors into key vectors for attention mechanism. We can initialize the values. We can start with the initialized values, and ultimately we keep on tuning the weights. So how do we initialize it? These are QW, QK, W, VW. These were the values 1010, 022, 0202, and 11. Three matrices. Now, the query Q, K key, V value vectors are obtained by multiplying the input vector X with their respective weight matrices. W query. Every Q, K, and V will have some weights. Weights are tuned with the iterations. Right? Initially, we can initialize randomly and keep on doing it as per the need. So Q is input, whatever input we have, and they have some weights. K again input and whatever the weights. And similarly, we have the V values. So this step results in the creation of QKV vectors that will be used to compute attention scores in the next steps. So come to the actual code now. We have to do Q X into W query. This is Q1 is 102 and Q2 is 222 and this is 213. This process is repeated. Initially, these are the random weights and we have to keep doing it. Ultimately, there's no change in the weights. So query Q is the matrix multiplication is a function that is already there in the NP numpy. And here we place X and W query. Got it? Q's are this and we have to randomize it. So this will be reaching to 102, 222 and 213. This is our Q. Q from this line, left side of the query. This is our Q and we have to multiply with the weights. So resulting vectors is similarly, we have to do it for the key. We have some keys. Here we assume that keys are 0, 1, 1. 3 keys. To have the simplicity, we have taken only 3 inputs. 4, 4, 0, 2, 3, 1. And we have some weights. And multiplied by that is coming 0, 1, 1, 4, 4, 0, 2, 3, 1. You can assume that weights are 1 unit only in both the cases. Here also 1 unit, here also 1 unit weights. Now we have to do it same for V. V, V1, V2, V3 as 1, 2, 3, 280, 263. These are the word embeddings, kind of word embeddings. Now again, we are multiplied with the values 1, 2, 3, 280, 263 unit values. Now we have to calculate Q, K, V vectors for each input. Multiply the input vectors by the weight matrices, W query and W key and W value to generate new one. Earlier, we had some values, we assigned the weights and multiplied by them and keep doing. So now, earlier we started with 1, 0, 1, 0, that was your input first. 0, 2, 0, 2, input 2, 1, 1, 1, input 3. And V1, Q1, Q2, Q3, 3 queries, 3 Ks and 3 Vs. Right? Now, compute the scaled attention score. The attention score is calculated as a dot product of Q and K and scaled by the square root of dk. This we have seen. This one, na? Softmax is equal to Q into K transpose divided by D square root of dk. In our case, what is K? In our case, 4. Now we have to calculate the scaled attention scores using the formula. Got it? So the attention scores are computed by taking the dot product of Q and K, then dividing by the scaling factor. The scaling factor may be considered as a weights. Earlier we took them as a unit vector, unit values, and we keep on increasing. किसको अपने को attention ज़्यादा देना है. The scaled attention scores are, these scores will be used to calculate the final output for each attention head. So here, scaled attention scores, Q into K of transpose, K का transpose, क्योंकि matrix multiplication है, 3 by 4 cannot be multiplied by 3 by 4, should be 4 by 3. And ultimately, हमें जो round लेना है, that is 3 लिया था ना हमने, 3 inputs and dimension was 4. So it's coming scaled attention score. जब हम once we calculate this thing, Q and K, and at the last we'll be multiplying by V with this one. These are inputs. These are Q, K, V's. This is matrix. First we have to have the Q and multiplied by K transpose. This is 3 by 4, 3 by 4, 3 by 4. And ultimately we are going to get 3 by 4 into 4 by 3 is going to get 3 by 3. So this is 2, 4, 4, 4, 16, 12, 4, 12, 10. This is scaled attention. Scaled attention. We have just computed attention scores. So earlier we started with this. These were the inputs. These were the key. These were the cues. I hope it's making sense. So step 4 is now complete. For example, the score of X1 is 244. This is 244. Scale of X1 is 244. Scale of second one is 4, 16, 12. And scale of third one is 4, 12, 10. X1, X2, X3. For all 3 keys, we have a score of 244. Got it? We started with 1, 0, 1, 0, 0, 2, 0, 2, 1, 1, 1. These were the inputs and these were the keys. So 2, 4, 4, all 3 keys, 2, 4, 4. So if we reduce it, it may be, these are the keys, K. So 2, 4, 4 is nothing but 1, 2, 2. 2, 4, 4 is nothing but 1, 2, 2. Scale attention scores for input number 1. So if we multiply it with 2, that is our attention scaled. So how do we find it? We scaled softmax attention scores for each vector. Attention score 0 is softmax, whatever we have received attention score to be passed into softmax. Similarly, for the first to be passed in the softmax again for the 3 inputs and printing the attention. So instead of this one, instead of 2, 4, 4, 4, 16, 12, 4, 2, 12, 10, now we have, after passing the softmax attention, after passing these scores to softmax function, we are reaching to these values. So what we are doing, we are applying the softmax function to attention scores, transforming them into the probability distribution to each input. That is the beauty of the softmax function, that every input will be converted into the probability. And the feature of the probability that the sum of every probability, sum of each the value will make it 1. Softmax ensure that the scores are normalized to values between 0 and 1, making them suitable for weighting the value vectors. These scaled attention scores represent the relative importance. If there are two values to be coming up, one is 0.6 and other will be 0.4 only, because sum is 1. And now we can see 0.6 is higher than 0.4. The word will give it to that question. I presume that the question is coming to the mind. What if both there are two values only and both are same, 0.5, 0.5, then what happens? So it's up to us only that we should take from the top to bottom or left to right, whatever it happens. Got it? And somehow we can apply, in case of that, we can apply any other function that may distribute 0.5, 0.5 instead of 0.51 and 0.491, something, 0.499. Any other functions, so that we can justify that this should come. Now, step 5 is complete. Softmax of the score of x1 is all three keys. We can calculate. Earlier it was, here, look at this. Earlier it was 244. Now it is, instead of 2, is coming 0.06, 0.46, and 0.46. If you add them, is coming, sum is 1. Got it? I hope it's clear. Now we have to calculate the final attention values for each input by multiplying the softmax attention scores by the value. So this operation gives us the final weighted representation. This value 0.06. So far we haven't made use of V's. We have just made use of K and Q's. Right? Still V's to be used. We had the matrix. So we'll start by calculating the attention value for the first input vector x1 by applying the softmax scores to the corresponding value vector. This V is nothing but the value vector. So once the calculation for x1 is done, we'll extend this process to the other input vectors x2, x3, and if we have many more, then we have to do it. So this step generates the final attended representation for each word, which is weighted sum of the value vectors. So here, earlier we had only softmax Q, K transpose divided by this first part only. Now we have to multiply it with V so that we get the attention. So once we have reached to this attention value obtained by this one, we'll multiply by V. And then you can see that instead of 0.06, 0.46, 0.46, we have other values after multiplying with this 123, 280. These are multiplication 263, and attention is 0.0633, 0.126, and so on. So attention 1, attention 2, attention 3. Got it? So in our Vaswani's model, we had D model of 5 and 2 and 8 attentions. Here we have only 3 attentions and our model is of 3 attentions. Our model is of limited resources. Now we have to concatenate. So for example, 3 attentions value for x1 for each input have been calculated. Input 1, input 2, these values are same 10, 10, 02, 02 we started with. And these are weights of keys and Qs 011, 440, 231. And Afterwards, we reached to 0.06, if you remember it, 0.46 and 0.46 softmax. And then we multiplied by V. V is 1 to 3. 1 to 3 is multiplied by 0.06. 1 को 0.6 से multiply करेंगे तो 0.6 input number, this was Q, 1, 2, 3. Yes, 2. 2 is multiplied by 0.06 is coming 0.12. 0.12, ये भी 0.12 है, it's 0.06, should 0.06. Similarly, we have 0.46 multiplied by this and so on. I hope it's clear. So you can assume that this is correct value. 0.6 nahi hai, is 0.06 is 0.06, sorry. The first value, my pointer is moving, is 0.06, is 0.12, is 0.12. So instead of 0.12, we have taken 1 for simplicity. Got it? So now, after multiplying with V1, for input 1, we are multiplying with V1. For input 2, we are multiplying with V2, and so on. So sum the individual attention values for X1 to generate the first of the output matrix. Now sum. आप इनको sum कर दिए, sum the result to create the first line of the input. So this is attention 1 plus attention 2 plus attention 3. Attention 1 plus attention 2 plus attention 3 for input 1. Similarly, we'll have the other inputs. First line of the output matrix. How did we reach to this one? You just calculate it. This is 0.6 plus 0.9 plus 0.9. 0.6 plus 0.06 plus 0.9 plus 0.9. 0.9 is 0.18 and something is added. Similarly, look at this. This is 0.12 plus 3.7 plus 2.8. 2.8, 8 plus 7, 5, 5 and 3 plus 2, 6, 6 plus 0.1. This is 6.68. Got it? Similarly, third can be calculated. 0.12 plus 0 plus 1.4. 1.4 plus 0.12. 1.59. Got it? So summing the attention values. Now look at this figure 1, that is summed result 1. So we have reached to this one, softmax. We reached to this one point. Softmax, then multiplied by value, then summed. So sum of attention Q, K, V values for input number 1. We are just talking about input number 1. Similarly, we have to do it for input number 2 and 3. Input number 1, X1. So it's coming 2, 7 and 1.5. Ye wali values. 2. This 1.93 is taken as a round off. 2. 6.68 is considered as 7. I hope you can see it from here. 6.68. Please read it. 6.68. We considered its round off is 7. And the third one is 1.59. Is considered as 1.5. It may have taken 2 also. So this is 272 or 271.5. These are the input number 1. This is input number 1. Input number 1 for X1. Similarly, we have input number 2, input number 3, and we have to follow the same sequence 1 to 7. What would if we have lots of inputs? Maybe hundreds of inputs possible. So we have to repeat the procedure. That's why parallelization works. These values will be derived using the same learned weights and attention mechanism as used for the input number 1. So again, we have to derive the weights and attention. So ultimately, the output, the resulting attention values for all inputs will be combined to form the final output. Got it? So for all inputs 1, 2, 3, in this case, we have taken 3 inputs only. We generate random attention representation within a dimension of D model 64. And the resulting attention for 3 vectors, and every vector, every input will have 64 this one dimension. So 3 rows of 64 each. The simulated attention output for head 1 is displayed. This is only for head 1. We have to do it for head 2 and 3 and 4 and 5. 4. Showing the 3 attention vectors of 64 dimension. For example, it is a 64 dimension and we have got 4 attentions. So again, 16 plus 16 plus 16. Or if it is a model of 5 and 2 and 64 dimensions, so 8 attentions, those will be concatenated. So we assumed that we have 3 results with learned weights. They were not trained in this example. We assume we are implementing the original transformer paper. We'll have results of 64 dimension each. So if we print it, step 1 to 7 for inputs 2, 3, similarly we get these values, 64 values for each input. So for input number 1, first value is coming 0.31 and so on. Second value is 0.991. For second input, we have 0.99. They are representing something actually. The values higher and lower, they are representing something. So we have to kind of a simulation to make it simple. So assuming that we have 8 heads and each producing for 3 inputs, each producing has got 3,64 matrix, 3 rows and 64 columns. Ultimately, the first attention is 3,64, second is 3,64 and so on. So ultimately Z will be Z0, Z1, Z2 and Z7. Each GI is nothing but 3,64 matrix. Now, how do we use it? So we have NP, that is our NumPy. It has a function random. So initially we can generate some values, some metrics using this. This is why so, because we have a shape of 8 heads of 60.
Madam, please unmute yourself. I think you are muted. I don't know why.
Ma'am,
You are unmuted. You are muted, madam. Please unmute yourself. I think.
Hello, Namita ma'am. You're not audible to us. Kindly unmute yourself.
Hello? Hello?
Yes, ma'am. Now you're audible.
So
Hello.
Madam, again you are
Namita ma'am.
muted. We can't hear. Unmute and then speak.
I'm not sure why it's happening. I'm not even touching my screen.
Yeah, now it is fine.
Okay. So those who are not getting may not be getting. I'm not sure what's happening. Again, it's unmuting, muting, unmuting, on and off.
Please, I think some of the person is doing this, so I request don't do this thing.
Okay. So one of the participant don't want me to speak. It seems so.
Yeah,
So
better to request that participant can leave, okay, so that other can be benefited.
yes. So for that participant, I'll share the slides. Most of the code is here, Python code. They can do it there. So still I have some time to speak, Dr. Anurag, or should I complete it?
Yeah, we can take the question answer after that. So
Okay.
it will be
So
better.
at the last, what we have to do, we have to concatenate of all the heads. So everything what we have seen is very small, only 3 inputs, right? So we have to do it for all the inputs and all the attention. For one input, we have to go for first attention, second attention 8 times, and then every input, every attention. So seems complicated, but looking at the infrastructure, computational efficiency, we can do in parallel. So this is 8 attention head outputs, Z0, Z1 and 7 till 7, and then concatenated. So these were the heads, and we get the output of multiple head with this one. So this is post layer normalization. Each attention and feed forward sublayer is followed by post layer normalization. This is what we have learned through the Python program. So this is at the last, this is the last, second last slide. The input to the layer norm is V is equal to X plus sublayer of X. So as we have seen, 6 encoder layers and 6 decoder layers. So every layer will have the output plus the original input. So layer norm is nothing but gamma V minus mu divided by sigma plus beta. What is mu? We understand that is average of all the values, and sigma is a standard deviation, and B is the bias if you have to add something to fine tune the model, and gamma is kind of a scaling. This is how we normalize our values what we have received. So the output from post layer network for the previous sublayer with this one, and ultimately we get the transformed representation of the input maintaining this model. Similarly, what we have done is to be converted to be think in terms of the decoder. So applications of transformers are NP model, BERT you have seen, GPT generative pre-trained transformer, BERT has only encoders and GPT is only decoder. Similarly, we have a text-to-text transform model. It has a encoder and decoder both. The applications of vision models is vision transformer, and similarly we have multimodal AI, clip, DALI, stable diffusion. These are the some popular multimodal models. It means they accept the text, audio, video, images, etc. in a different kind of forms. So ready to use transformers with Hugging Face are available. Tasks like machine translation. Machine translation is kind of we ask the question in English, what is to be done in German or French, English to Hindi, Hindi to English. This is example of machine translation. So open multi-head attention sublayer Python code. You can do it. Save the notebook. Ensure Hugging Face transformers are installed with. And if not, that you can do pip QQ install transformers. This is the code. I have written it here. Then conclusion, the transformers revolution It has revolutionized our life with the help of transformers. Simplified transactions means just a conversion task and uncover long distance dependencies in the language. Because NLP has got two parts, NLU and NLG. This is about the NLU, understanding the context. By removing RNN, they don't need RNN, LST, MCNN transformers, only use the attention, maybe self-attention or multi-head attention. Multi-head attention is kind of a one attention, self-attention that is already there. Apart from self-attention, we can have other attentions as well. Key innovations in this one transformer is positional encoding, and similarly we can have multi-headed attention, that is masked. Advancement, the transform model has sparked in a new generation of AI models with tools like Hugging Face, making it easy to implement just lines of codes. So if some students are sitting here as a participants, they can have a small project to understand in a different context, maybe sentiment analysis or any other idea. And the domain may be different, but the idea is same. So these are the references I have used for understanding the transformer. Sorry for the font issue here. We have it as. So this is, I can conclude it here. If you have question, you're welcome. So these two books are available online, PDFs are available. And I request everyone, those who want to use transformers, please read the paper. Attention, all you need is the paper by Vaswani. This is very good transformer, very good paper. Those who know it bit in advance, then it's easy to understand. And the lecture of almost 130 hours is 1.3, 1.5 hours. But those who are the beginners, first time they are learning, may be difficult. In case of need, you can later also connect with me. My email ID.
Ma'am, can you please send the link of the paper?
Sure. Link of the paper.
Now I would like to request to all participants, kindly ask your question. Kindly raise your hand or either write your questions in the chat box.
If you need to search, madam, then you can share the paper later. So I will share them with the group also.
Yes, definitely. That is a good idea. I'll share with Dr. Anurag. He'll share with all the participants. It's easily available. Just type the keywords and that is there. It's not a big deal. You just type the title of the paper and the author Vaswani by Google. That is enough.
Scholar.
Yeah.
Okay, Sanjana, so you can conclude this session.
Oh, okay. Sir, Dr. Veena have some question. Dr. Veena, are you in the meet? Kindly ask the question to the speaker.
Ma'am, I was asking about the paper only.
Okay.
Paper we will
Right.
share later
Okay.
on over
Yeah,
the
yeah,
group.
yeah. I'm not able to find. I have shared with many, and it is available online. No issues, Dr. Veena.
You just type the name and
Yeah,
author, so you will search.
author's name. It is available. That's how I found. I'll share definitely.
So Sanjana, you can conclude session now.
Okay, thank you, sir. A big thank you to Dr. Namita Mittal ma'am for your insightful session on nut and bolt of transformer. Your detailed breakdown of transformer architectures, their inner workings and practical application provided us with a strong conceptual and technical foundation. Understanding this fundamental component is crucial for advancing in generative AI, and your session has truly helped us grasp the more core mechanics of these powerful models. We deeply appreciate your time, expertise, and the clarity with which you explain these complex concepts. Thank you once again for an engaging and enriching session. And that brings us to the end of day 3. A huge thank you to our speakers for their bright and brilliant sessions on advancing training and transformers fundamental. Today we will delve into the core mechanics that generative AI so powerful, and also these insights will be valuable as we move ahead. To all our participants, your curiosity and engagement continue to make this FDP a truly interactive learning experience. Keep up your energy. Kindly join us tomorrow at 6 p.m. sharp. It is going to be another exciting day. Thank you once again. See you all tomorrow.
Okay, madam. Thank you.
Thank you, sir. Thank you.
Thank you for session.
Thank you, Sanjana.
Okay.
Thank you, participants, for listening patiently. Thank you.
Thank you. Thank you.
Okay, madam. Good night.
Good night.
Thank you, ma'am. Thank you. Wonderful section.
Acha, participant, there is one small request. The objective of FDP program is only for learning. Learning is the primary objective. So if a speaker is there, please don't ask directly, share the video, share the PPT. So we will request them if they will share PPTs with them. I will share it with you with the group. And how we will share the videos, I will decide later how it can be shared with that number of participants, and definitely we will do. But please don't ask directly to the speakers. They are not doing the video recording. We are doing the video recording. So definitely we will do all the things at the end. Regarding feedback, I told you many times it will appear in your portal at the end and you have to fill that. Only after filling the feedback you will get the certificate. And meanwhile you can note down feedback of every speaker so that later you can fill that. And regarding attendance, I am not doing anything. The MS team will generate the consolidated report of attendance at the end by every in and out session. So I request you to please attend the session, focus for attending all the sessions, because all sessions are very much important rather than typing many messages during the session, because I am also attending the sessions and all our volunteers are also attending the sessions. Okay. And regarding the joining link, I'm surprised still people are struggling with the joining link, and we put one session if you have any difficulty, and we passed all the instructions how to join if you are not able to join with the app. So please follow the instructions, join in time so that there should not be any difficulty during the session and people should be disturbed. Okay. Our objective is learning. Okay. Thank you. Thank you for attending.
Hello.
Okay. Now you may leave. Good night.
Okay, sir. But somebody removes in between. No, why they do that one?
No, there are many problems. Definitely one of the participant is doing this. And
Okay.
there are some restrictions in Teams, so we cannot do that. So it looks very bad. And among us, one people is doing this.
Okay. Because
So
like yesterday
definitely,
also same issue. Today also
yeah,
like somebody
some
removed
some
me again. I
person is doing
rejoined.
this. Some person is doing this, and it looks very good, bad impression. Some speaker, we arranged very good speakers for you, and you know what participants are doing with them.
Yes. I know. I understand.
So it is very embarrassing. Actually, their logins are not from our institute domain, so we cannot make them organizers. So this is the restriction here. Okay. So if somebody is doing, please don't do And if you are not interested, please don't attend. But don't do such things, because definitely either you are a teacher or a student, it doesn't look good. I think you can understand this. And please don't write multiple messages regarding the attendance. Attendance is taken by MS Team. If you know about MS Team, it automatically generated. I can't do any manipulation. Okay. So we need not to fill Google form. Already Excel file will be generated by team. And please chat box only use for typing your questions. Otherwise speaker will be confused what people are writing, because they are only coming for their lecture only. Okay. You may
Hello.
leave now. Who? Yes.
Yeah, this is Soumya Tripathi.
Mm-hmm.
Sir, I have one suggestion. Like you told us, like first day, second day, now even today, third day, people keep on asking about the attendance and the feedback. What you can do in the WhatsApp group, you can write the message about the all the details, like feedback will
See, all
be.
the details are sent multiple times, and
No, you can send that message and you can pin it in the WhatsApp group. So every time if a
madam, it is
person
pinned
asking, you
only.
can
I
do
don't
that.
know when you have joined. Regarding feedback, if you are applying in the ATAL portal, all the instructions are given. Please look carefully. Okay.
No,
So
I'm saying
see
ki everyone
feedback.
is asking about it. I'm just suggesting ki you can write the whole message, ki what gonna
Madam,
happen, and you can
please,
print it
please
out in the
listen
group.
carefully. Our objective is that to attend the FDP. This is not your part for feedback and attendance. If you will not fill feedback, automatically your certificate will not be generated.
Yes, true, sir. Correct,
Sir,
sir.
I
Very-
know.
We typed multiple times over the group. I don't know people are seeing or not.
No, many are
Yes,
attending
sir.
only for
That's
attendance.
what I'm
If they are
saying.
bothered about
Even
that,
Madam,
let them
please
step
told
one.
first day.
see the people. Madam, please listen carefully. People, those are asking these questions. They will always ask the questions. Similar questions are asked by multiple people after passing many times. I have given instructions regarding attendance, even today also over the group.
Yes, it's very
But still
disturbing.
people are
That's why I'm
asking.
saying ki keep on. Yeah. It's very
Correct, sir. Sir,
disturbing. I have to
you
open
end the
every
meeting, sir.
time. I
Sir,
have to open the chat box.
Sir, you end the meeting because there are few people, they only join for attendance. I know that very
Yeah,
well because
yeah,
even I have
madam.
conducted.
Madam, if you will see the group, everything is written in detail. I don't know why people are avoiding. Only two questions are asking in the group: attendance or feedback. Feedback is our responsibility. We will take whenever it is required. Your objective to attend the lecture very carefully and get knowledge whatever people are providing. This is your primary objective. Rest of the things taken care by us. Okay.
Yes,
So please, you may leave the meeting so that we can get the attendance. And thank you for joining,
Yeah.
and please join in higher number at time only. Okay. Initially people join very less and slowly it is increasing in mid of the lecture. You may leave, please.
Thank you, sir.
Okay, bye.
Thank you, sir.
Participants, please leave the meeting so that our volunteers can get the attendance. Otherwise, they will be very late.